Starting the live stream. Morning, Henry.
Hey, Tridge.
Good morning. And Bill and Jeff. Starting to get the gang together. Just waiting for the live stream to start.
How goes it?
Great.
Awesome.
Morning, morning.
Made some great presentations yesterday.
Now I need to mute the live stream that I'm watching so that I don't end up hearing myself with a 20-second delay. All right, so live stream's now open, and now I'll go and pop it on Facebook and on LinkedIn. Okay, it's up on Facebook, now LinkedIn. Really surprisingly easy to do all this stuff. Okay, that's good. That's done. Now, chats, I'll need to pop into the other chat and saying, right, now have I forgotten anything? Have we got it all up and running? Oh boy. Oh, I'm gonna sleep well after this.
You forgot Instagram.
Oh, I don't do Instagram. You can do the Instagram, Louis. And I'm leaving James to do Twitter.
Last time I did Instagram was 5 years ago.
Uh-huh.
Last time I did Instagram, it was 5 years ago.
Yeah, I've never done Instagram. It just hasn't been my thing. Works surprisingly well with the double microphone and remote desktop thing that I'm using. So, you know, have my Windows box displayed on my Linux box and get allowed for the virtual background. Really works well. Morning, Paul. Now, let's see, we've got Tom, hopefully has written his talk now, and Julio Mendoza, then Henry with documentation, or Henry and the whole team with documentation, really. Documentation update. Now, you sent me a link to those slides, I think, Henry. Can you send me that link again and I'll pop it in the agenda? I think that's a particularly important one for people to be able to follow through the slides themselves. It looks like Henry's still trying to get audio.
Oh, I'm sorry, but I passed the way around your your talk about systems update, Rich.
No worries. It's, I think, a wise decision. I mean,
No, I fell
probably,
asleep on the chair. Come on, I fell asleep on the chair.
that's it. Yes, that's right. It's well known that I do that to people.
No, sorry, Rich.
It's
I was
fine.
had lots of interest to see it, but oh my God, come on.
Yeah.
I was up at, it was around 1 o'clock for me, and I was up from 5:30 a.m.
Right.
So
Ouch.
long days, Rich.
Yeah. I'm looking forward to the EQF talk from Rob later, Rob Mahoney. That's I'll show you, Randy,
Oh,
that
yeah.
the skywriting thing that we did.
No.
Oh, I popped a picture of it on the channel. We've got the letters EQF written skywriting above Spring Valley with a copter running S-curves.
Oh,
And
yes, I did see that.
yeah, and then they captured all the video and the IMU data from ArduPilot, and they basically got that replaying the video and the IMU data to reproduce the path from
Oh,
purely
cool.
vision data, which is really
Cool.
cool.
Awesome. Looking forward to that. Yeah, last year's was a great talk as well.
Yeah, it's taking them some time to get to the point of actually integrating it. It should be pretty soon we start feeding the data back into ArduPilot and have it as a fully open replacement for the Intel cameras, or as an alternative, system, just running on relatively cheap commodity hardware.
Yeah, that sounds great. Well, we're already now on the ArduPilot side after all the
That's right.
P265 work that we did. So
yeah, indeed,
in good shape. I'm sure it's tough, the with all the autonomous cars, there's so much money being poured into the closed source solutions.
Yeah,
like the Intel cameras, like on Rishab's talk yesterday, they're getting so much better all the time.
Yeah, that's right. Those depth cameras
it's all
are incredible.
Good to have lots of solutions open and closed. But
yeah, the other thing that the ANU group is really into is event cameras. And at the moment they're very expensive, but eventually I think event cameras are going to be quite interesting for ArduPilot. Are you familiar with those at all? So an event camera is a camera there. They only give you information about movement. So they basically track events, but they can track them very, very fast. So it's like a differencing camera, if you like. If you just search for event cameras, and there's some incredible capabilities you get with it. But instead of giving like a complete frame image all the time, it gives you what's changed, but very, very rapidly in incredible detail. There's some fantastic demo videos if you search for it, of the sort of thing that you can do.
Yeah.
So one of the examples of the sort of project is a drone sitting hovering, and somebody throws a soccer ball at it as hard as they can, and it can actually pick up that fast moving soccer ball and dodge it.
Wow.
Because it can pick up just that movement, and it's far too fast for the depth cameras or the other visual cameras to pick up. But an event camera has no trouble at all picking that up and then working out how to just dodge that ball.
Cool.
So if you're wanting to do something like flying in a forest and dodging branches and trees and things, everything's so fast moving, the only way to do it with the normal vision system is to fly relatively slowly.
I see.
Yeah, this is but the volume of data that has to actually be processed is a lot less, because it's only showing you things that are actually happening. Anyway, do a search for some videos and you'll see what I mean.
Cool. guess people need to start thinking about the roadmap as well.
Yeah.
Session right at the end, but you know, if people, I think, you know, James or I will probably whip up a Google spreadsheet, and then the developers
Well,
can.
we should probably go back and watch last year's roadmap and just see how much of it we've got done, sort of tick it off and have a comparison.
Yeah.
We've got the big tick on the S-curve stuff, which is fantastic.
At least for rovers.
Yep, and the rovers and the wider CAN adoption and the new sort of AP perf stuff. I think we've ticked off that. There's quite a few things we have ticked off from last year's roadmap and commitments. But I think it'd be worth going back and rewatching that. It might be something to do over this lunchtime, the break between the two sets of talks today, to watch that and then make a dot point list of what we said last year and then, you know, what we're aiming for in this next year. All right, now I need to make the speakers for this morning. So if you should ping Tom, I haven't seen him. He's the first speaker.
We've done okay actually on the roadmap. Some parts obviously we haven't done, but I've gotten through quite a lot of it actually.
So, okay, so Tom says he'll be ready in 5 minutes. We might be starting just a few minutes late. We could shift the talks around by a few minutes, and so Julio, if we wanted you to go first, would you be ready?
Yes, if it was the case, I have no problem.
All right. What do other people think? Should we shift things around and give Tom another hour? He's obviously just finishing off his slides.
Okay.
Yeah, it's probably a good idea then.
Goodbye, Tom.
We could even have Tom after the documentation update. All right, I'm going to shift things around a little bit. So, okay, so let's see. So just give me a second while I rearrange the schedule slightly. So Tom says 1 hour will be fine. Okay, so Julio, you're now up first.
Understood.
Okay, that's fine. So I've now shifted around the schedule. I'll just put up an announcement to say that we're shifting the schedule slightly. Okay, that's great. And in which case, I need to give you, Julio, the ability to share your screen. So just let me organize that for you now. And I'll just do some more co-hosting on, I need to organize my own co-hosting. Sorry, I'm not as well organized this morning. Going to take me a minute to get this up and going. I need to make Randy a co-host so he can record. And I will make Craig a co-host as well. He can be the adult in the room. And okay, all good. And maybe Louis. Great. All right. I think we've got a good set of co-hosts there for the co-hosts really help. If I have a network outage, then it'll automatically keep the call going. And as long as at least one of the co-hosts is still online. And I'm not expecting a network outage, but you never know. Okay, so good morning and welcome everyone. And I'm just going to start the recording now, ready for the first session. Great. So good morning and welcome everyone to the third session of the ArduPilot 2021 Developer Conference. And we had a fantastic series of talks yesterday. If you weren't able to catch them yesterday, then all of the videos from yesterday's talks are now up on the playlist, the Developer Conference 2021 playlist on the ArduPilot.org YouTube channel. And there's actually multiple copies of each video. There's one's recorded with individual videos per talk, but there's also both the live stream complete session and there's also a video recording of the complete sessions done separately. So they do have slightly different properties. The complete session ones have the talking heads, so you can see the person's expression as they're describing the what they're working on. Whereas the individual ones don't have the talking head on it. So you've got a choice of how you want to view the talks. So this morning, we've got another great lineup. And we're starting off with a talk by Julio Mendoza, talking about ArduPilot in Latin American research. And after that, we're moving on to Tom Pittenger with an AP Perif update. Then Henry and the rest of the dev team together are discussing the documentation, particularly the state of the ArduPilot documentation as we get prepared for the 4.1 release. And then we have a talk by Rob Mahoney and Peter Van Gore about the ANU visual odometry system, which is looking really exciting. And finally, we have the new vehicle, Blimp support. Michelle Rousseau talking about Blimp support in ArduPilot. So we're going to kick off first of all with Julio Mendoza. So over to you, Julio.
Hello, everyone. I'm going to start with my talk. Okay, first of all, I'm going to share my my screen. Okay, I'm going to show you about the ArduPilot in Latin American research. I'm Julio Mendoza. You can find me in UNAM, IPM, and these web pages. Okay. First, the context. What we are talking about Latin America. Latin America are developing countries or regions based on the classification of the International Monetary Fund, whose official or predominant language is Romance ones, and Neo-Latin language as Spanish, French, or Portuguese. This is Latin America. Second, a second segmentation is based on drone research and drone development, in this case, aircraft, watercraft, and wheeled vehicles. This is convenient in order to zoom into particular countries that had more research on the field according to the IEEE, have more patents and developments on the field according to the WIPO, and have more industrial activity related to the field according to companies as DJI. Also, this shortens my slides because despite the fact that each one of the other countries has a lot of particular projects, they are not so numerous. So in this case, I'm going to talk about Mexico, Colombia, Brazil, Argentina, and Chile. Next. What do we do? Okay, we do things with budget and with not so much budget. When we have budget, we do military and aerospace application and companies. In this case, most of them are focused on airplanes. Examples are Embraer from Brazil and a little company called Oaxaca Aerospace from Mexico. This is with budget. But with not so much budget, we do vehicle robotics. most of them with Chinese and open source components. For example, the quadcopter kit in our region, the quadcopter that you can see in your monitors, could be bought in our region with 1 month on a standard researcher salary. So it's expensive, and we require Chinese and open source components. In this case, the famous PixHub 2.4.8 and the ArduPilot libraries. For this reason, our research are mainly the algorithms. In this case, controllers, filters, estimators, artificial intelligence, patents and intellectual property, and a lot of text, included books, articles, etc. Here we use all kind of free software. When I say all, since the open projects to piracy, disunfortunately, which of course is more accessible than hardware and physical components. Let's move on to what the aforementioned countries develop. Argentina. For this country, what I found is that they developed a lot of research at each university, and there are two main researchers who are the regular and main reference in this nation. Both of them are experts in mobile robotics and control. Their research focus at vehicle formation, tracking algorithms, SLAM, visual surveying, and agricultural robots, also interfaces design, software and autopilots. In this case, this person is Ricardo Carelli from National University of San Juan. He does mobile robots, drones, and their applications. Currently, he obtained his PhD in Mexico and is a regular collaborator of the Brazilian researcher that we will see later. Here you could find his personal webpage. He is Ricardo Carelli. The other is Juan Giribet from University of Buenos Aires. He does drone fault tolerant flight, indoor navigation methods with Wi-Fi, and developed his own autopilots, a kind of Argentinian PixHub. He was with the Argentinian Space Agency, and of course, here you have his personal webpage. Okay, now let's move to Brazil. As I told you, Brazil has its own airplane manufacturer, Embraer. So they produce commercial and military airplanes. Most of their aerospatial research engine is aimed to this industry. However, concerning to our war of unmanned vehicles with ArduPilot, they also have notorious wars. Some examples are, and you have Edison Piñatón de Freitas, and Douglas da Silva Jr., Lucas Vago Santana, Alexandre Santos Brandao. Here are their universities, and well, they particularly develops sailboats with ArduPilot and coordinated robotics and multi-agent systems in the same field. In the case of Lucas and Alexandre, they have been working with a lot of indoor navigation, flight formations, low transportation, and sensor fusion algorithms. They applied the parrot drones, but we must remember that ArduPilot has support for those vehicles, and that this result can be extended to other vehicles. They are from Brazil. Also, Brazil has a culture of robotic competences and makerspaces place where they develop and teach drone applications. An example is Drone Lab from Brazil. Here you have some print screens. They make competitions, they make tests, and well, this is a very known place in this country. Let's move to Chile and Colombia. Chile and Colombia are cases where the research on robotic vehicles and drones are available all over the country, but most of the projects are under the supervision of three entities: the Army, private universities, and private investors. Inside all the available papers and theses, you could find from modeling and control to environmental, agricultural, surveillance, and delivery applications. A good example of what they do is the Colombian Kiwi campus and their Kiwi bots that they are designed for delivered food. But well, this is an example that is made in Colombia. In the case of Chile, when talking about robotic vehicles, it is worth mentioning to Javier Ruiz del Solar. This is a prolific researcher in mobile robotics algorithms. You can find him in University of Chile, and here you have his webpage. Okay, concerning to Colombia more than specific people, the aforementioned institutions are commonly found in all the Colombian drone projects. As I told you, military and private founders. But of course, if you want a name, here you have the contact of Rafael Padilla. He is part of the UAV War Federation in South America. And well, if you want to know more what is Colombia doing, contact this person. And now with Mexico, due to the fact that my country is neighbor of the US, we also have a triple approach, as in the case of Brazil. So we have researchers, developers, and industrials. As the other countries, all Mexican universities develop drone projects, but we interact with a kind of a local center called Sinvestav, and concretely, UMI-LAFMIA. In fact, all of us have a kind of participation with this center, like partners, teachers, etc. Here you have their webpage. UMI-LAFMIA is a dual Mexican-French research center on drones. They do terrestrial, aircraft, and watercraft. They offer master and PhD degrees. Their leader is Rogelio Lozano, one of the most important Latin American researchers on robotics and drones. In fact, you can find around 6 books and a lot of papers about the topic written by him. Other people is, other person is Jordi Munoz, concerning to the ArduPilot world. Originally, he founds 3DR, but now he's with Mayan Robotics, and he produced a lot of models of autopilots, including his own Pixel version, all compatible with ArduPilot. So if you want a novel autopilot, you can consult his webpage. Also, as I told you, we do industrial cases. We develop application for the small and micro-scale enterprises. For example, this company that offers solutions with mobile robots. In this image, we can see a kind of Rossi from Jetsons, but used for transporting glass bottles during their manufacture process. In this case, they use a combination of Cube with ArduPilot. And other things that we have in my country is a public high school with a technical specialization on drones called CONALEP. They are stated in Sinaloa, and well, they are for the young people, for the young researchers, for high school researchers. In summary, in our countries, we developed a lot of robotics vehicle applications where in general, a couple of researchers, a research center, an institution, or a company are our main reference. In this case, for budget, for knowledge, for distribution, or diffusion. And almost all of the researchers are related with the aforementioned ones. Most of our research has agricultural, rescue, or military applications. And well, ArduPilot and Pixel represent around about 30% of the tools, because we develop our own autopilots at 10% of the cases, and the rest of people use Arduino, Raspberry, or direct microcontroller coding, in this case, AVRs or PICs. In general, we use open or free technologies. Our culture of web sharing, in this case, GitHub, YouTube, etc., is not so usual. Instead, we produce more papers, local conferences, and theses. With the exception of Brazil, we focus mainly in education, software, and algorithms. Industrial application and large-scale projects are reserved to military or commercial airplanes, foreign agreements, or small-scale industries. Currently, technologies arrive into our countries 2 years later. Years ago, this happened with decades of separation. That's explaining why, for example, we talk about technologies that are a little old, 2 years. Okay, about me. I'm a mechatronics engineer with postgraduate degrees on robotics and control at UNAM and IPN, two of the most important Mexican universities. I'm an enthusiastic about ArduPilot. In this topic, I had written 2 books, one in 2020 and recently in February of this year. The first one is also available in Korean, and coming soon, it will be available a Chinese version. Talking about the 2020 book, it is available in Press Springer, also in Golden Valley in South Korea, and coming soon in China Machine Press. Here you have their corresponding web pages. The book is based on previous version, as I told you, 2 years of ArduPilot, but it's a good reference for beginners and intermediate users, even advanced ones. It consists of 3 parts. Elementary concepts and commands, where I talked about basic input and output sensors and actuators and more. The second is advanced commands with multi-copter applications. In this case, UR and telemetry, SD memory usage, time commands, and more. And we finish the book because we are a lot of co-authors, as you can see, with real-time concepts and commands, where we talk about the real-time scheduler and some examples. Continuing with this, for some reason, reader report that they couldn't find this in the included software. So here you have it. If you have the opportunity, please print the screen. And I continue with the other book. The other book is available since February of the year. Equal with the same publisher, Apress Springer. Here you have the web page. This book is by Excel, a short and complete course with a maker and scientific approaches. It is designed for assimilating at least 2 years or 3 of your knowledge in just 6 or 12 months in order that readers could develop their drone projects in a faster way. Also, reader could extend their knowledge to other kind of aircraft and vehicles, and it has 5 chapters. Drone concepts and design, where I talk you about components, standardization, history, etc. The second is drone modeling, where you can find kinematics, dynamics, allocation models, in this case, useful for mixer design, linear and nonlinear models. Drone control, where I talk you about linear and nonlinear approaches from smooth flight to geometric control and acrobatics. The fourth chapter is drone simulation, a faster way for simulate a drone by using Simulink. And I finished the book with the chapter of drone implementation, where I talk about tips for filtering, telemetry, programming, etc. Why did I write these books and some suggestions? Okay, there are a lot of material about Arduino and Raspberry, maybe hundreds of books, courses, and magazines each year. But what I found with ArduPilot is that our community only had the discussion forums and the main web page. And well, we must remember that there are people that requires a book or live courses. As the only SDK with a simple real-time scheduler, I wanted to spread this knowledge, this software to the world. Also really think with the ArduPilot, but I think that develop a kind of easy to install and use interface as the Arduino IDE could be amazing for our community. Also with direct examples, including a kind of Hello Motor code as in the Arduino IDE. Maybe mocks and official courses. In fact, I will pay for ArduPilot development courses and even for official certifications of ArduPilot. Maybe an official ArduPilot's AutoPilot, as in the old times, the 2020, no, the 2012 AutoPilot from ArduPilot. Maybe a kind of design your vehicle model in the mission planner interface that could go beyond the standard vehicles available. Well, these are my suggestions, okay? And that's all that we do in Latin America with ArduPilot. If you had questions, come on.
Well, it's cool to see the the overview of how ArduPilot is being used. It's always as a developer, it's always quite encouraging to see how it's being used. To see the code that you've been writing actually get put to use. So that was really interesting to see, especially like the sailboat stuff. I wasn't expecting that. So thanks for that.
Yeah, thanks very much, Julio. So where does the community, that sort of Latin community, tend to congregate? Is it using our discussion server, discuss.ArduPilot.org, or do you have your own communication channels, sort of language specific ones perhaps?
Well, as I told you, this is not common among us, but what we do is conferences. For example, we have a one called Red UAS that is developed each 2 years. And in this kind of conferences, we talk about our developments, about the courses. In this case, I found ArduPilot through my partners at UMI Lafnis Investab. Well, as I told you, they teach me this knowledge, and I spread this knowledge to the world through my books. This is the way that we communicate.
Right. Okay. I was hoping there might be some sort of more, how the users actually get assistance. I'm guessing they use our discussion forums, but I was just curious if you had your own forums or something like that. I'll put a link up to the source code that I noticed that in the slides, it seems to be an image, so it's not clickable. So that's the link to the GitHub repository they've got there. And just because they seem to be image links, you can't actually click on them. And so the first one, I haven't typed that in yet. That's a slightly harder one to type in. So if you could possibly either update that to be a text link or pop it in the chat so people can actually follow that link.
Yes, I could share.
Yeah, it's just a little bit hard to type in that that hash, in the Dropbox hash accurately. So it'd be nicer to be able to go and have a look directly. All right. So are there any more questions for Julio? Well, okay. So thank you very much again, Julio. Much appreciate your talk this morning. So Tom, are you ready to start a bit early?
I am, yes. Sorry. about the delay there.
Fantastic. All right. So in that case, I'll need to grant you. So do people want to break it all or go straight on? We've only been going for a little bit, so I think we can probably go straight on. I'm just going to find Tom in the list here so I can add him to the ability to. There you go. There you should be able to share screen now, Tom. Okay, and I've put a link to Tom's presentation into the schedule. So if you want to follow along the slides there, you can. And of course, there's a link to Julio's presentation there as well. So over to you now, Tom.
Hi, well, thank you, everyone. My name is Tom Pittenger. I am normally actually the plane maintainer, but I've been doing a lot of AP Perf stuff lately, so I've kind of got the opportunity to do this, do the update for AP Perf. So it's actually on the wiki now, has its own web page entry. We have our own logo, and ta-da, that's what it looks like, AP Perf. And here we are. Oops, next page. Where's the next page? Here. Okay, so what is AP Perf? It's one of our new things. So I want to make sure I share with what it is. It's a relatively new project that we have offered within ArduPilot. There's several different hardwares that are off the shelf. I'm going to talk about all the features of it, what's now, timeline, things in the future, how to get to use it a little bit, some development details of how to dive in and start using it and develop your own things, and then depending on questions or whatnot, maybe I can do some demos and compiling it and something like that. All right, so what is AP Perf? Basically, you just build ArduPilot without a vehicle. Normally, if you build ArduPilot, you get all these other things with it, like object avoidance and GPS drivers and IMUs and all these things. But you have a main loop that it runs through to basically check serial ports and all these sort of services it's running. So what this is a much more minimalistic version of that, where we have it has its own main loop. So it's basically you compile it as AP Perf as the target, and it's just its own main loop running just a little small tasks you want. That allows you on the build to give you a much smaller build size, and really cater to smaller memory footprints, smaller or slower CPUs, and just basically do just the little things you want. And this allows you to make hardware that's very specific to just do a little task, and then leverage all the infrastructure that we have with ArduPilot. You get serial ports and buffers and DMA and UAV CAN and all the protocols and all these other drivers. So there's a few products out there that use an F103, STM 103. And it can build for that, but you're really going to have to finagle a little bit and trim things down. But basically, you want to start with at least 256, and that runs comfortably a few features, no problem. But if you're going to do it, I'd actually recommend doing like an F4 with 256K or higher, just to future-proof yourself. But if you're making a given hardware for just a certain task, it's, you can get by with 256. And because there's so much hardware out there already, you can actually take a Pixoc 1 or a Cube or whatever, just off-the-shelf ArduPilot, and use it as an AP-Prif hardware target and do development from there. And all you need to know is just what pins are connected to where on your hardware, and you're done. Here's some examples of some off-the-shelf hardware you can get. Hex is coming out with some products that are using it. So they've actually been contributing a lot of the code to build out a lot of the infrastructure on it, which is really nice. That's with the help of Sid and Michael DeBro, or Michael Oborn. And so, and robotics has been one of the first markets, I think. They had the F103 and they came out with a 303. Now they're coming out with some newer products. J-Drones has some, I think CUAV does, but Maytech I know has a GPS product. It's fairly easy. If any manufacturer's already made a STM32 based ArduPilot compatible thing, then it's fairly trivial to make an AP node. One of the reasons we actually kind of went down this path of making AP-Prif was because manufacturers or users were using ArduPilot as a vehicle. So you just load in copter into a Pixoc 1 or whatever target, and then it'd be right along as logging sensors or being some sort of node to do something. And it was some people were hacking at that to make that work. And we realized, just bring that in as an actual feature. So here's all the different kind of libraries that we and features that are available today. So just recently we did a Tribios update, and that's part of that allows us to have multiple cans. So we can have like can 1 and can 2. As of just a month ago or two, it only had single can support. So now it has multiple can, just like our other vehicles offer, as in can 1 and can 2 physical ports. You can make a node be a GPS. So if you have a U-Blocks or whatever kind of receiver, it can plug into your node, and then primarily the nodes talk UAV can back to your vehicle, and so it just emulates as a UAV can GPS or a UAV can magnometer or a barometer or a whole list of different things here. So these are all the libraries that we've brought in and added support for, and they are generally it's a feature to UAV can converter. So I think we've added a few UAV can specific packets, but a lot of these are already supported in the spec as is. But it gives you a nice little tool, like for example, RC out. With that, this allows you to have multiple can ports on your vehicle, and you can via just can or run them out to some other target, and then that can then turn into 16 GPIOs or whatever out on the end. So it's all controlled over CAN, and all the hardware's kind of done there. You can just put a Pixoc or whatever on the end. So one of the earlier features we added was the LED and buzzer type support. And so Toshiba and NCP and NeoPixel, those were and buzzers, those were added as you can do them individually, and it'll fit in the 128K. But if you basically add any other features, it kind of fills up your 128K. So adding the notify library is the proper way. It takes up more memory, so it doesn't fit in the 128. But doing that, you basically have all the features in the notify library. So that includes your on-screen display stuff, whatever LEDs and NeoPixels and RGBs all at the same time, and buzzers. In fact, the buzzer itself I've used on the vehicles I use at Kraus Hamdani Aerospace. We don't have a buzzer on the aircraft, but it's nice to know when it reboots and stuff, if you're doing firmware updates or whatever. So everything on it is CAN as much as possible on all of our new development. And so I can just plug in a cube on a carrier board that anywhere on on the end of the wing or something, and then suddenly I have a buzzer that I can use to know when it reboots, which is kind of convenient. And all the nodes work with the UAVCAN DNA. So that's the auto assignment for the address or the CAN ID. But things like ADSBN parameter. Oh, I have parameters twice there. So you can configure all this through parameters, and I'll give an example later of how to do that. There's a mission planner has support for talking to this over serial or USB or TCP and UDP. That sounds a little funny, but I've been using some serial to IP converters, and then I can actually do an SLCAN on a serial port, feed it into Mission Planner, and so over UDP traffic, I can do firmware updates on my peripherals, which is just amazing, and configure them and all that. The whole battery monitor is there, so you can actually this as a standalone thing can be used as just a smart battery. So you'd have lots of different batteries or inputs or calibration, whatever. You can just put a little small chip on your battery, and then suddenly you have a UAVCAN compatible battery. So that's nice. You can create the names of in your hardware defined. You can create the title. So when you show up, you can see all the different peripherals on the bus, and so you can name it whatever you want. And then so on. There's airspeed, rangefinder, and so on. There's all the typical things we offer that right now. Things we're missing, however, there's no SD card support. So there's no login. There's debug that's over the UAVCAN, but you can't write anything to the SD card yet. So there's just no storage there, which means you don't have things that also use that, such as scripting and such. There's no Mavlink, sort of. So there is Mavlink support, for example, with the ADSBN. So this is, with ADSBN, it's talking Mavlink to like a UAVionics ping receiver, but it's basically just looks for that one packet and just parses the one thing. So the whole chunk of reading packets is not normally in there. So it's kind of a one-off. And so I think there's actually two different places we parse for packet, but we're not normally processing packets at this point. There's been work done on IMU as an external AHRS, but I don't believe there's anything in there in master as of today, but I think it's pretty soon. But that's going to be a giant target where this little node can be placed anywhere, and it can become a triple redundant IMU sensor or whatever, just as a standalone node. So that's really nice. UAVCAN 1, of course, ArduPilot doesn't support that quite yet, but that's definitely on the roadmap of wanting to be done. So we're having to use some of the older protocol, the version 0.9, and the DSDL, the packet descriptions are all from the older one. So we'd like to change it to that, but we're on the 0.9 now. ADSBN is supported, but not ADSB out. So that's a kind of a weird one-way thing that that's asymmetric. And FDCAN. So this is the fast data where you can send data at 8 times faster, actually. So that's coming in with some of our new Chibios updates, and we'll be adding that soon. It's kind of in the pipeline, but it's something would be really nice to have, but it's just not there right now, but coming soon. Some of these in progress things that I know are under development is CAN protocol translators. For example, I have an ESC, like a KDE CAN. You could have a KDE CAN ESC, and but my ArduPilot is using two UAV CAN ports to talk to a whole bunch of different peripherals. I don't want to dedicate a CAN protocol I don't want to dedicate a whole port to a protocol. So my AP periph, it can have one port coming in as UAV CAN, and then the second port is KDE CAN talking to the hardware. So it can basically translate there. So there's been work there. It's not quite ready to go into master, I think, but there's pull requests available and stuff. MPPTs is kind of a fancy battery that I'm using it across sundown airspace. That's for solar panels, charging batteries. It's basically, it looks like a smart battery, but it's charging from a solar panel. So it's a smart solar panel instead of a smart battery. Output for 32 servos. There's technically support in master for that for vehicles. So it's kind of halfway there for the AP-Perf nodes, but I don't think there's any hardware that quite supports it. But I believe it should at least accept the messages for it at this point. So it's kind of halfway there. Right now, the hardware-defined.dat is how we describe all the hardware when compiling for Chibios, and it's a little confusing because the hardware-defined bootloader and the app are a bit redundant. So I have a branch where I've kind of combined that into a hardware-defined common, and then your hardware-defined.dat is actually just it includes common, but then gives you just app-specific things, and then your bootloader is just bootloader-specific things, but your hardware is all described in the common. So you don't have to copy things back and forth or have them different or have too much redundant stuff. It's easier to maintain that way. And that's actually more of a ArduPilot in general, like an infrastructure that I'd like to kind of move forward with for all hardware defines. It's just problem with that is it affects every hardware that we have, so it's hard to test those to confirm they're working. So we might need to do those one at a time or something. But that's those. I have working versions of those on hardware that I'm using. IMU nodes. I know the IMU node. There are some people that have versions of that going at or that have prototype hardware that they're using this for. So I'm sure it's just a matter of time that they'll get it as a native feature. Native ESC, yeah. So David May is a new hire here at Krause and Downey Aerospace, and he's actually working on ESC as a standalone native device that's based on AP-Perf. So it would be actually adding a new feature to ArduPilot as an ESC. So we'd actually have an open source ESC that can run our algorithms, but also run all of our infrastructure and UAV CAN and serial ports and feedback, and also act as a battery to measure currents and all that. So he's working on that, and really excited about that. So that'll be a big plus for AP-Perf as far as ArduPilot being like a brand of ESC, sort of, or at least the software running on it.
So I'm curious, Tom, is that VESC based, or is that a new implementation of the ESC, is underlying maths and control of ESCs?
Well, so David May is doing this as he's just finishing up his university, his engineering degree, and so he's doing this as a senior design. And so he's doing the maths and whatnot as part of his project. We've looked at the VESC, and it's a bit confusing as far as how it all kind of works. It's not very clear. But agreeably, I haven't looked into it deep enough to really spend the time to understand it. But so I'm thinking it's not going to be based on that, but it's open source, so it's one of those things where we could look at to see if there's some things we can learn from it. So
the other one that's worth having a look at is the newly released AM32. I don't know whether you've seen that at all.
AM32, no, I haven't heard of that.
It's a new open firmware for BLHEL32 ESCs, just recently announced, and might be worth having a look at as well as another basis for the underlying maths. It supports things like D-shot and bidirectional D-shot already, which are, obviously, if we're doing a perf ESC, we're going to be doing CAN as the primary protocol, but it's got quite a few nice features.
Yeah, I mean, BLHeli is also open source on some of their systems. So
the BLHeli, yes, but that's in assembly only. I don't think we want to do an assembly-based ESC, and it's very hard to follow assembly.
Yeah, I was going to say you'd have to see what it's doing, but you can't just copy and paste the code.
I've looked through BLHELIS and it's really quite hard to follow. But the AM32 is written in C, as of course is VESC, so they're a better basis.
Yeah, well, I mean, this is it's kind of just starting to work on this right now, so I'm sure he'll see this video and have your good ideas and look into it further.
On just to add to that, FOC drive is a big win on an ESC if it can be, if whatever we're doing supports the basis of that. Like, and that VESC does support FOC drive.
Yeah,
Right. So that's the idea, is to leverage all the technologies we can and be open source in a way that's very adaptable and easy to integrate into systems.
I think FOC, I mean, do you mind a little bit of an aside and discuss this a bit, Tom, during the middle of your talk? Would you like to leave it to the end?
That's okay. What's next is the future work. Yeah. So.
Yeah, so it's like FOC is I think a very worthwhile feature to have, but I wouldn't want it to be required as in the only. That's been some of the weaknesses some of the ESC firmware we've had have been only FOC, and that can be quite difficult to tune and get it to work on different combinations of motors. So having like trapezoidal as the base, but then optionally put in FOC, is there any particular reason why that wouldn't be doable, Leonard?
Oh, well, the reason why I like VESC is it does exactly that. It's got, you can set it up, trapezoid, FOC. It's also got a lot of automatic tools in there that allows you to use the ESC to make the measurement on the motor to define the FOC. So there's actually a tuning process, like an auto tune. You effectively go through, you connect the motor, you go through and you run a test, and it goes through a test on the motor to measure the required components to build the FOC model that you can then, so it takes about 5 minutes to set up a motor for FOC using a VESC. It also supports sensor feedback into the ESC. So you can add sensor, like a positional, like a Hall effect sensor to take the position of the motor and do a sensor driven motor. So basically VSC does like all three of the main sort of drive topology. So
interesting.
Yeah,
so we should probably have a separate chat with David May, and because I know Sid's very interested in this, and Leonard's obviously interested, and I'm interested. I think a whole bunch of us are interested in a ArduPilot hosted ESC project, particularly with CAN.
I can tell you that ESCs are the single biggest barrier for
reliability,
commercial aircraft, and
efficiency.
We were able to sort of have this firmware that we could keep on driving forwards. I wouldn't be surprised if it went the same way as the ArduPilot in the longer run, where basically if you wanted a reliable industrial aircraft, you had to run Ardu ESC.
I think it is an absolutely key thing, and I'd love to have a chat with David, and Sid and I have been discussing it a little bit. It's something that I think it's very worthwhile putting effort into. And test infrastructure. We need really good testing for ESCs. It's hard to test them really well, as you well know, Leonard.
Now, keep in mind that this is one of those things where it's baby steps to get something new like this working. Day one, just open loop is great, and then you can add to it, right?
It needs to have the right sort of structure to be able to do some of the others. But it'd be a really good discussion. We should probably let you get on with the rest of your talk now, Tom. It just piqued my interest very strongly.
What's that, Peter?
Peter?
Oh, I'm sorry. I should mention that we have previously had a fairly active open source attempt at doing this called Open Motor Drive, which I know very little about, but could potentially be another resource.
Yep, that's true.
That was FOC only, I believe, and it was quite difficult to tune, was my memory.
Yep, but fixing that might be better than starting from scratch. Sorry, Tom.
Yep. Okay. Yeah, and that's with the John Challenger.
Great. All right. Thanks, David. Thanks, Tom.
Future work. All right. So things that we'd like to do that are roadmap type of things. Promote this as a first-class citizen. So right now it's actually living in tools/APPRIF. So we'd like to migrate it over to just into its own folder, kind of like how Plane and Copter and Rover are. Also, there's a whole lot of code being handled in the can.cpp file. So we should probably try to, abstract those out a little bit more. A lot of the features are wrapped around pound if defines to enable it. So it's just so the file size is real small. But a lot of it's kind of just thrown into this can. It's still commented or if defined out, but it's a lot of the handling is kind of happening in one place. So we might want to rearrange this a bit. So that's it works right now, but it's kind of getting unwieldy as we're adding this onslaught of features. And with an onslaught of features, you also get lag on the wiki, on the documentation. So we need to make sure we keep up with that and get that going and update the feature list. And one of the problems we have right now with that is we don't have the param descriptions. So in normal vehicles, they're semi self-documenting by each param. You have the description and all that, and then that we have on the wiki. We scrub those files and post it, and generates that on the website. So you see that for various versions of our released firmware, and so it kind of other GUIs can pull from that. So when they see a parameter, they can match it up to a whole paragraph description, and none of that happens right now for APPref. So it's a bit, you kind of have to dig in the code to look. Most of the parameters have description stuff. So if you look in the code, you can see all that stuff, but it's not on a web page or anything quite yet. Also, it would be nice that a nice to have feature is on the vehicle when it boots up. It would be nice that you can embed a version of your node code into your vehicle code. So when it boots up, if those don't match, it just pushes that version out. That allows you to always have a repeatable system where if you update one system, it then updates your whole system. You don't have to go through each one and possibly miss them or whatnot. Also, the incompatibility problems where if one's on one version and the other one's not, maybe it doesn't work the same way or respond to it. You can have regressions and such. So it'd be a nice feature to optionally do this, so it can scan everyone's firmware and make them all new, or at least make them all match. So you always have a vehicle code matches this node code, or I shouldn't say they match, but I should say it matches the expected firmware. All right, and then also just implement more and more stuff. We have lots of other libraries that we could add in there. Our library folder has gotten quite long, so it's like 100 different things now or something. So we can just keep adding more features into APPref as they become necessary or needed. So how to use it? There's Mission Planner has added a lot of really good support to it. So if you go to the setup tab and then go down to UAVCAN, there is this page, which is normally blank, but you would click on the SL can. SL, I think, is serial link can or serial something can. And that's basically wrapping the CAN packets into a serial friendly thing that you can send over the serial port. And so other GUIs can ingest it or talk to it over a serial port and interact with your CAN bus. There's two main tools for that. There's the UAVCAN GUI tool, and which is from the uavcan.org folks, and Mission Planner. On Mission Planner, if you plug in a device like a cube, it gives you two different serial ports. You'll notice it says like Mavlink or SLCAN. So that's how you use it on here. Is on here it says on the top right it says COM20, but if you clicked on it and pulled down, it would actually say COM20, or it'd say or Cube Orange SLCAN 20. When you do that, you automatically start getting all this data. So this is actually what an example of other devices. So I have a HERE GPS and a EMLID Edge GNSS GPS receiver. So I have two GPSs there. I have this one here, which you can see is this is the ArduPilot itself, so it's kind of seeing itself. And this is another one. So I have a Cube Orange perif. So this is actually running a Cube Orange, and it's looking at a different Cube Orange that's running the perif firmware. So you can see all these things, and the menus light up. You can look at all the parameters. So these are the parameters, how you configure things. You can read, write, and all that sort of stuff. But also from this menu, you can click to upload a firmware. So just you go menu, and then I think it's update, it says. But after you compile the code, you send it the .bin file, and it will firmware update the devices, which is nice. You can communicate to this. So those are the two software systems, but on hardware, you can use any ArduPilot hardware. I'm not sure what version we started that, but we've had it for a few years. So circa 2017 or 20 or so, we've had this SL-CAN support, and that allows us that with any ArduPilot that has CAN, you can plug it into your bus, and it'll populate and look at all the CAN bus around the screen like this, or on the UV CAN GUI tool. There's also something from Zubax, who also, same folks that did the UAV CAN GUI tool. They sell something called the Babel, which is a similar thing. It runs the SL-CAN protocol so you basically get over a USB port, right? So you can get it's a CAN to USB converter, so you can see this stuff on the screen. As far as development wise, we recently added a soft in the loop instance of it. It's somewhat minimal now. I think it only just runs the GPS. If you want to do testing on it, you have to add in the features manually right now. But there is support for that, so it is there, and you can connect to it locally and see all the data and interact with it and do that work. Bootloader wise, it embeds the binary of the bootloader inside the vehicle or inside the app firmware, just like the vehicle code does. So you can update your update your bootloaders. And the bootloader itself is a little bit bigger than normal bootloaders because all the interaction on here is happening through CAN. So the whole CAN stack has to be in there. So that pushes the file size above 16 kilobytes. So in most of our targets, 16 kilobytes. For like F4s, 16 kilobytes is a block, so we can run it that big. But on an H7, the smallest block is 128K. So it doesn't matter if your bootloader gets big; it all takes up the same amount of space. It takes up one page. But for targets like the STM32F3s and 4s, if you use an AP-perif bootloader, you have to make sure that the bootloader size is, you reserve enough space to be at least 24, or I think it's 26K, or just 32K, whatever. It has to be more than 16, basically. So depending on your target, you can look at it, see how many pages are available for that. But as far as development, it's fairly easy for a developer to, if you want to use it, if all the current features are okay with you and you just want to make some hardware, you just you make a new hardware define.dat, and then you just include like an F303. Let's say that's the chip, you include the F303 perif hardware, and that describes kind of a generic system, and then you can kind of just turn on features from there, or you can modify it to change pins around or whatnot. But it gives you a nice head start. So several other products actually do that. They include that and then just tweak a few things. The files are actually quite minimal. So we have inside the ArduPilot tools, AP-perif, this is it. This is the whole folder that runs everything for AP-perif. You'll notice that the can.cpp is 71K, but everything else is pretty small. And that's just a testament of the infrastructure that is leveraging in ArduPilot. It's literally just including a library, like you'd say in the AP-perif.h, you would say you'd include AP rangefinder, for example, and it just sucks in the whole rangefinder. Now you just run the rangefinder update and the init, and magically you got a whole rangefinder system now. All the drivers and all that are there. So it's pretty amazing the infrastructure you get for the minimum amount of work you get, and then it's just all the work you need to do is just adding that one feature. That's why, for example, the ESC talk we had earlier, you'd make that, you add a new feature in and just run the update on it. There may need to be something special for DMA handling for fast sensor feedback or whatnot, but all that's there, all in place, and you can even spin off your own threads and all that, just like any other library does. And in fact, all the libraries do that right now. So, for example, like I said, the AP rangefinder, if it's an I2C bus, for example, all that comes in already, and it spins its own thread off for the I2C bus it's on, and all that. All that's in the library, right? This has all been abstracted out into their own libraries in such a modular way that AP Proof just includes it and then calls update, and ta-da! So quite amazing. And that's all I have. I don't necessarily have a demo to show, but I can go through the steps to show some hardware defines and or compile it and just show what's necessary to kind of tweak one. I was wondering from the audience if anyone had any requests on what they'd like to see.
G'day, Tom. There is one from the audience asking how hard it would be to add OSD to a periph node.
I haven't tested it, but I believe that's already there.
Okay.
Yeah, you just include the, or you enable AP perif.
No, we can do MS. Well, we can do MSP output, which is,
Oh, I'm sorry, OSD.
OSD on-screen display. We don't have in any of the peripheral nodes yet. It would be certainly doable, but though the problem with that is populating all of the fields, right? Because the OSD wants to have a whole lot of data. So unless the peripheral node can get all of the data to populate the fields, the OSD is going to end up being pretty sparse. So there's a whole lot of precursors. We would have to be publishing that state information onto the bus from the ArduPilot. So it's certainly doable, but it's sort of not all that useful until you have all of that state information, published onto the CAN bus in the first place.
And all one limitation, information is all of ArduPilot state, really.
Yeah. So one limitation
you can have pieces of it, but
one limitation we have is actually all this data has to get squeezed through the UAV CAN port to it, right? From the vehicle to the node, it has to tell it everything. And there is information like that. That's essentially your HRS information that gives you your location, heading, and all that sort of stuff.
Well, if you published Mavlink to LIM down and encapsulated on UAV CAN, then you could have the OSD in the AP perif.
Yes, so that's one thing that I've actually done that a couple of years ago, was doing a Mavlink over CAN translator, or not CAN, the tunnel, I should say, so that a device on the other end only talked to Mavlink and it just accepted CAN packets and just popped them out as Mavlink. Yeah, it's not high bandwidth, right? It's 38K, 56K, but that's what OSDs were before we integrated them on board the chip. They were Mavlink dongles. Yeah. So you can get almost everything normal person would want in an OSD with the Mavlink to LIM. Yeah, which reminds me, back here, available today, I think I said OSD on here. OSD, yeah. So I don't mean OSD on here. What I meant to say is the OLED screens.
Right. Okay.
Yeah.
Yes, you notify on the OLED, although again, what information you're going to display on the OLED, because the notify subsystem, I mean, things like buzzer and things and LEDs, no problem, because we publish that from the ArduPilot, but we don't at the moment, for example, publish the attitude. And, we don't publish a lot of other information that would normally be displayed on an OLED or on an OSD. And yeah, I'm not sure going the Mavlink route, encapsulating Mavlink is necessarily the best idea, because we end up with a fairly complex parser of that Mavlink, and the original OSDs that were based around Mavlink weren't as good as our current OSD. They didn't provide the information in the same level of detail, and they were a lot less efficient. We constantly had little troubles with exactly what data they could display and how they could intuit it, and coping with planes versus copters versus rovers, etc. So it'd be an interesting one to think about. my first reaction is that I'm going the Mavlink route probably isn't the right way to do it.
Yeah, well, I do have a pull request from 3 years ago when I tried that, and
yeah, I think supporting a serial service is very worthwhile. I think we should go back and revisit that. But it shouldn't be a Mavlink service; it should be a serial service. And so it's not Mavlink specific. You should be able to do basically a serial port expander is far preferable. And we did have a version of your PR, I think, Tom, that did that. That did it as a general serial port expander.
Yeah, in fact, I added that to the UAV CAN spec. So there's a thing. I think I renamed it, but at one point it was called tunnel. So you could tunnel just bits, and so you can make it be SPI or I2C or whatever data you want over that tunneling.
Yep.
I think they call it bridging now or something like that. But yeah. Yeah. Okay. So how about we take a quick look at, or how are we on time? We're at.
I've still got plenty of time. So we're scheduled to finish this in another hour because we finished the first talk a bit earlier than expected, and so we actually have plenty of time. So if you want to, but we don't have to use all of that time. We can take a break, or we can move on to other discussions.
Well, let me pull up a hardware defined as an example to just demonstrate that a little bit. So let me get this out of the way. I will go here. Let me see. I have the Zoom thing hiding. Let me try and hide this thing. It's not hiding. Oh well. So here's an example of the hardware defined for F303M10070, which is a new product that's coming out from MRO. So it's a new GPS device, or GPS, and well, let's find out what it does. So what they did is it's an F303 STM32. So on this file, you basically just create this directory, and then you had it ArduDefine.dat, and because it's already using this, it has a similar pinout. They just copied that, just included that, and we'll look at that in a moment. And then they named it, so they just called themselves this, so it would show up on your mission planner or whatever list you're using for your GUI. So this is what it looks like. And then they just define the SPI and barometer, just saying what address to use. So it just defaults to that when it tries to talk to it. And then this is the guts of APPREF. You just enable these features. So it's turning on the mag library, it's turning on the GPS library, and it's doing the RGB LEDs, but without notify. So that means it only adds that one feature as opposed to the whole library. One downside of doing the whole library is you get a whole lot of parameters of a whole bunch of stuff, where doing like this, you just get, you hard code to say, just do this, just do this one pin. And as well as the airspeed, right? So this one device is going to be capable of looking like all these devices all at the same time. So it'll be, you can hook up your barometer to it, and I'm sorry, your differential barometer for your airspeed and whatnot. So then let's look at what it's including here. That is this guy here. So that's the F303 perif. So this one describes a bit more of the details. This looks like other hardware defines. If I go back to this for a moment, you notice that this is all that M Robotics had to do. They did this. They wrote this part here to describe what features they wanted, and suddenly they have a new product that magically does all these things. And they just made sure that they connect the dots on the schematic, and the dots just matched previous versions of available hardware, but they could have just wrote the whole thing by themselves. Look at, copy this data and just remapped it to whatever pins, because there's no pin map in here. You notice they use the existing one from here. So it was fairly trivial to just say this device does these features and ta-da, you're done. There's just in a few lines of code. And
it's worth spending a minute on the DNA, the line 6 and 7 there, where it discusses the choice about dynamic DNA is dynamic node allocation. And that whether you want to do, whether you choose 0 or non-zero is quite a subtle choice. And so some of the devices have chosen non-zero and some of them 0. Do you want me to describe that, or do you want to describe the reasoning behind that?
Well, yeah. So it's the well, yeah. Why don't you
Yeah,
jump in on that?
So it's basically this is something that the vendors do struggle with a little bit. So it's worth understanding. You can either set up a peripheral node so that it will automatically be assigned a node ID on the bus by the flight controller, because the flight controller runs what's called a DNA server, dynamic node allocation server. And if you set it to 0 there, that means it doesn't start up with a node ID, and the parameter node ID starts as 0, which means it'll sit there waiting on the bus until a DNA server assigns it an ID at boot. And that's the default for most of our peripherals. And if you want to be able to connect multiple of the device on the bus, you have to do it that way. So for example, if you're selling CAN bus GPS modules and you want your users to be able to trivially just plug in 2 of them, and they automatically get assigned different IDs, then you'd want to default that to 0. But some of our vendors have deliberately chosen non-zero, which means it comes up with a fixed ID, which makes it easier for some users and harder for others. The advantage of using non-zero is the peripheral doesn't have to do CAN bus. And so, for example, Maytech did this for their GPS module and airspeed module. And the reason they did that is the peripheral device, the Maytech GPS and airspeed sensor, also supports MSP output with no CAN bus. So if I've got one of these airspeed sensors here on my desk somewhere, or maybe I don't have one handy, they want to be people to be able to use it with only the MSP protocol and no CAN bus. And so if you had DNA enabled as set node ID 0, then it would never come up on MSP because it'd be sitting there waiting forever for a node ID to be allocated. So you couldn't use it with just MSP. And the other subtlety in this, if you do dynamic allocation, it's a little bit harder for end users to work out which, for example, which GPS is which can really matter if you've got one GPS on the end of one wing and the other GPS on the end of the other wing, and you're going to get the positions right. Then the first thing you'll probably want to do when you buy those GPS modules is to actually change the node ID parameter, which I think Tom is just showing there now. If you want to bring up the parameters from one of those ones, Tom, go and set so that you actually set the node ID under M. There should be a node ID parameter there, so
I don't think it's in here. It's not a parameter.
Well, there is a node ID parameter. There should be.
Well, for a vehicle there is, but I'm not sure. Oh, you're right. There's
CAN node. Yeah. So that's the node ID parameter. Yeah. So it's doing DNA. It's 0. But if you want to actually have multiple GPSs and you want them to have non-zero positions relative to the center of gravity, then you'll want to set that node ID on each GPS so that you can then assign positions in a stable fashion. So anyway, that's the little subtlety about the DNA configuration in AP perif nodes. And you've got to actively make that decision as a vendor as to whether you want to grab one of the 127 possible node IDs as a fixed ID, or whether you want to be able to just do it as dynamically. In most cases, you want dynamic, but there are some cases like the Maytech one where the right choice is to make it a fixed ID because that makes it easier for the majority of your users.
Yeah. So for example, here, so I just connected to a vehicle here. So these are all the CANs for the normal vehicle. You can, for a GPS, because when you have 2 GPSs, you can use that as a heading, but you need to know which one's left, which one's right, or you don't know to swap the positions and all that. So you can say this one here, this one's definitely, when you boot up, it needs to be node 1, or I should say GPS 1 needs to be this guy right here, and GPS 2 needs to be this guy right here.
Yeah. And the support, so Sid has been working on patches to make it easier then to assign the GPS node IDs to a particular GPS ordering in our GPS library to make that position assignment easier, because at the moment it is quite tricky to get that right. Basically because the CAN nodes can come up in any order. We can't control what order they appear on the bus. All right, so anyway, I just thought an aside on DNA would be useful, Tom.
Yeah. So if you notice here, there's a F303 Kraus device, and that is just an MRO node, little F303 node. And so I just did made my own and added the features I wanted to, you know, slapped in it has pads for I2C and SPI and whatever. So I use it for my own purposes. But so I can identify it now with my own name just by adding that one line in here, or just by adjusting the line. So I would make a new target here. So in hardware define folder, I would just say, you know, Kraus 303 or whatever, and I'd include this, and then just make my own name and add the features I want to add, and ta-da! But let's go down and look at the more under the hood stuff. So the F303 perif. This is more what the other vehicles would say. So if you were to do like an FMUV2 or 3 kind of thing, you would see all these things. So you'll notice the flash reserve is 26K on this one. So that's using the on the F303, it's using 22K plus 4 for storage. So it's reserving that ahead of time. And there's parameter storage, which is nice. So that's actually built right into the flash of the STM32. So you don't need an external EEPROM or non-volatile. This is the key, that when you include this, that basically changes how everything looks at this. That treats it as a kind of, you know, different device, which is nice. But you just, your clock frequency, you can set clock timing stuff. You just tell how big your flash drive is. If you have multiple serial ports.
It's worth mentioning the clock frequency a little bit more, the oscillator. The one thing that I've worked with quite a few vendors bringing up new AP perif devices, and one of the things that often causes problem is getting the crystals right. And so we've now added support for putting 0 as the oscillator frequency. And what that means is it uses the internal oscillator on the STM32 instead of using the crystal. And that's particularly good for debugging. If you've got a crystal problem, you can turn off the crystal and just use the internal oscillator. So you don't need a crystal at all. You don't need to attach one, and get it working like that, and then get it working with the crystal. Because it's surprisingly common how often there are mistakes in prototype boards with crystals from multiple vendors. It's one of the more difficult things to get right. And so being able to specify a 0 crystal is quite useful.
Yeah. And then the UART stuff, this is very traditional to how other devices work, where you can have your UARTs in whatever order you want, and so serial. So this actually ends up being the parameter. Let me actually bring that up here. So if I was to go over to perf here and look at the parameters of this on my cube orange, I don't know offhand which ones are built into it, or which features are on or off right now. But for example, you can tell it what COM port it is. So, you know, COM port 1, 2, 3, 4 kind of thing. Yeah, so if you have ADSB or rangefinder and all these things, you just say, I want to use COM 1 or 2, and that's logically the first one or the second one. So this particular device, for the basic one, it's COM 1 and COM 4 is available. So it'd be serial ones. I'm sorry, not COM, serial 1 and serial. Oh no, I'm sorry. This is serial 0 on this one. So serial 1 and 2 are not available. The first one's for the GPS. Typically, the defaults are your first one's your debug port. Serial 1 and 2 is your telemetry 1 and 2, and then the next one would be GPS. So this particular target uses that as a default, just so the rest of the library kind of uses it. All the defaults kind of line up. But yeah, just setting the PA pins to say you want to up it low and set your SPI clock to PA5 or whatnot. You can look through all the other hardware defines you can see all the other targets here. These all have a hardware defined file for all targets we have. and they just basically just describe the hardware. And it's a lot easier to just take something that is similar to your device and just copy it and then just tweak what you need. You usually don't need to worry about too much about the process stack and stuff like that. Just make sure your pins match, and when you compile, it will sanity check a lot of those things for you. Speaking of which, why don't we do that? Why don't we compile something here? Let's see. Oh, I can't see my text. Let me just close that. There we go. Oh, not that. That's a bad one to run. Let's just nuke that. So if I'm trying to run a F303 dash, let's see, we can do the M. Well, let's just do the cube orange ORN. So if you hit tab on that, you should get. Oh, it's not capitalized, but it still runs. So if your hardware defined was not correct, then you get all kinds of errors there. So I'm just running the target like normal to just grab this as whatever the directory name is on this list. So we could do the Matex 764 wing. Well, that's actually 743 perif. Actually, why don't we do that as an example? Let's change that to say Matex H743-perif. Okay. And then you just run AP perif, ROF AP perif. So this is interesting. The AP OSD was loading on that.
Yeah, that's just because of the include of the hwdef.dat from the cube orange, and that has the wildcard pattern for the OSD fonts. So it's embedding the fonts, but it won't actually link the OSD library, so you can't do anything with it. So it's really just wasting a bit of flash space.
Well, if it's not linking it, then it won't. Then
no, it will still embed them. It'll still embed it because it's a
the files get embedded. Yes,
the fonts will be embedded, which wastes flash space, but the library won't be.
Right.
The library will be built, I would expect, but not embedded.
So let's look up this target while it's running. So we can look up this. So on this one, it included the main Matex, and then it undefined a few things. So the cube orange perif does the same thing. It just includes cube orange and then removes a few things. It does not have a fat file system. Like I mentioned before, there's no SD card support. But here, it's a battery, it's a servo, rangefinder, ASD, ADSB. It just magically runs all those things and get those features. You can also tell it how many instances that you want to limit for your system. And I think these have to be one, if I recall, for AP perif right now. I'm not sure how well it handles multiple GPSs and multiple rangefinders. It may actually work, but I don't think I've tried that recently. And, one also nice thing is there's something here like the HAL AP perif ADSB port default. So if we go into here, so in this hardware, they probably have a label that says ADSB or something like that on port 3, on serial port 3. And the idea is we can go into in all of our defining here, we say if it's not, and this is how we use a lot of the defines. If we don't define something, it'll give you a default. But we're saying on this hardware, we do use it. So down, actually, when we enable this in the library, it gives you the correct default value for that device. So for that particular one, instead of just using our global serial port 1, we said, no, this one, we want you to use serial port 3. So that's a neat little thing that we can, that's part of all of our libraries, is a lot of them are like this. And, same thing with a BOD, so you can default 0 or whatever. whatever the parameters are. Yep. So how'd that build go? Yep. So it works. And that's that. So that now, what did that give us? That gave us a build / Maytech and bin. And then there we have the traditional files here. But if we want to upload that over our device, you would, like over Mission Planner, you give it the bin file. And that's pretty much all there is to it.
So what you were mentioning earlier about uploading the firmware, currently we typically use one of the user interface UI tools, and I completely agree that the idea that we should be able to do a mass update of all the peripherals. If you've got a whole bunch of ESCs, like 8 ESCs, or updating each of the 8 individually would be quite painful. So I've actually been thinking there's a couple of ways we could do this. One is subdirectories on the SD card, where the subdirectory named after the string node name, and then you could have a firmware in there, and we could support a bootloader client inside ArduPilot. So that's one approach. Another would be a TUMPFS. If we extended AP file system to have a temporary file system support, then you could actually FTP a firmware, Mavlink FTP a firmware to the AutoPilot into TUMPFS, and then send a Mavlink command to say, now please upload that file to all of the nodes, all compatible nodes. And it would have to know that the node was compatible with that firmware by using that, probably the string identifier, along with the board ID. And that would provide quite an easy way to do a mass update of your ESCs, for example, because I think otherwise it'll be quite painful.
Yeah, because in our aircraft, we actually have we're going to have several AP-Pref devices throughout doing various tasks and everything we can. We have minimal other stuff. So it would be nice to be able to maintain that when you do an update, to just kind of have your whole system on ready to go, and then you just control them individually for parameters.
Yes,
you can do different things.
One thing we have done recently is we now log the firmware string and firmware version of every CAN device that ArduPilot sees on the bus. We log that in the onboard log, and we can optionally send that over Mavlink as well, which is quite handy, so that you can then, is the new CAN-D message, CAN device message in the log, and that at least allows you to tell now whether your devices are up to date by what firmware they're running. But the next step of having an automatic update of the nodes, I think, is essential for much more widespread and easier adoption of CAN devices.
Yeah, although all the information is available, it's just a matter of automating it, right? Because when we look at like down here, when we look at this, we get version numbers and hashes and all that right there. So it's over the bus already. It's just a matter of the AutoPilot's just ignoring all that stuff right now. Yeah.
Well, it's logging it at the moment, but it's not totally ignoring it, but it's not using it to do an automated update. And I think firmware update basically we need to implement the bootloader client inside ArduPilot, so that it can go and it's the file. There's an API within UAV CAN for doing file transfer, and we need to implement the file transfer to be able to transfer a new firmware, put it into the bootloader and transfer a new firmware.
Well, and the beauty of this is, we make a library and then we just include it on both systems, and they both have the same system. That's the beauty of this. It's all shared libraries.
It's already implemented in AP-Pref because it's already does allow.
That's true, I guess.
So it's already got the server side of it there to receive the firmware, because that's how we do updates currently. We're just missing the side within ArduPilot to be able to send the firmware without using a GUI to be able to update firmwares from the AutoPilot without intervention from a GUI.
Yep. All right. Anything else? If not, that concludes.
Just a quick question. I mean, is there any hope of ever porting this onto hacker boards like like Teensy and that sort of thing? Maybe some ARM-based Arduino or something like that.
Well, right now it requires Chibios to really for all of our parsing and stuff. So and so that's limited to our STM32s right now.
Yeah. Well, there is a Chibios port for Teensy.
There's Chibios for it, but we don't. All of our scripts are right now basically hard coded to only support STM32s.
Yeah. So someone has to do all the work of the driver.
Yeah, and that's based on that Chibios the hardware defined system. It runs through scripts when you do the configure, HAL configure. I'm sorry, WAF configure. That's ran through scripts comparing the hardware defined chips against the chips.
Yeah.
And so we only have knowledge of STM, or the tools only have knowledge of STM32s right now.
Yeah.
So
So no one's really looked at porting that across to other.
It's perfectly doable to do a different, a non-ST chip. We do recommend at least having 256K of flash for a peripheral node. We do have some nodes that are 128K, but it's quite tight because you basically got two CAN stacks you've got to include. One is the bootloader and the other is the main firmware. And for reliable update, you really need 2 copies of that stack. And that limits, the amount of, you can't really go down to very small flash size devices.
Yeah.
But yes, it would be quite a lot of work to do a non-STM32 target, and probably not worth it to put a lot of effort into other than STM32s, because they, apart from the current chip shortage of STM32s, there's a bit of a problem. But apart from that, they're fairly ubiquitous and pretty good value.
Yeah, it's just you can just imagine this would be really useful for that community to have something like this, I think. So.
Hi guys, it's Buzz here. Just thought I'd butt in for a minute and say you're all wrong. It's already done and it works. Now I have a bleeding edge, very, very experimental port of ArduPilot to the ESP32, which is actually running on FreeRTOS, which has been around for a little while now. It's been around for maybe a couple of years. But about 2 weeks ago, I was able to just barely get a version of AP-Proof running on the ESP32.
Ooh, fancy.
So
very nice. Congratulations, Buzz.
If you're interested in bleeding edge, nasty code that crashes lots, but runs on something other than an STM32, then come and see me. Back to your normal program.
Thanks, Buzz.
Yeah, thanks, Buzz. Yay, Buzz.
I guess I don't know if this is the right place to ask, but it's kind of related. Has anyone ever looked at running AFDX protocol or supporting AFDX protocol on ArduPilot?
FDX?
AFDX bus protocol. It's an Ethernet-based protocol that's used on big planes, but
I know nothing about it. So I imagine that a whole bunch of developers are now Googling AFDX, avionics full duplex switched Ethernet.
Yeah,
well, there's a Wikipedia article.
It's the backbone bus that Boeing and Airbus use. It's just that it's Ethernet based, and most of the STM chips now support Ethernet. So it would be
what's it called?
AFDX.
DX.
Yeah.
Sure.
I mean, it's
Okay. Well, I mean, the basic attitude of the ArduPilot project is to support anything for which there is demand from our users. So, if there's interest in this and if it's useful, and somebody puts their hand up to put the time in, then certainly. It does have to be something that, there is enough interest that it's worth maintaining, because typically the maintenance cost of additions like this is higher than the original development cost. If you'd like to, prototype support for this, at the moment we don't support Ethernet at all on our STM32 boards. Obviously, we support it on the Linux-based boards where it's nice and easy to do Ethernet, but on the STM32 boards we don't. There is a couple of efforts. There is actually an effort underway to add Ethernet support on STM32 boards for ArduPilot, and I think that's likely to happen in the next year. But it's a little bit early to be given status updates on it. but I
But
think
just when I see Tom, wiring a whole aircraft up with CAN, I mean, that seems, it's not outrageous to imagine that somebody at some point would want to hook up, an FTX component, although they're hugely expensive. A really high-end drone might want to work with an ArduPilot flight controller or something like that. Would be.
Yeah, I mean, it seems like if it's 802.3, then that's that's super standard. It's just a matter of the data going over, I guess, and timing. But existing hardware seems to do it.
But I mean, it opens up a high band. You get 100 megabits per second and low latency. So,
yep,
it'd be really great to have.
Yeah, having so the problem where peripherals right now with Ethernet is you have a kind of a infrastructure hit with having Ethernet in each box, and it makes your peripherals bigger.
Yeah.
Right. So that in with Airbus here, that's okay. You don't even notice that. But on these little small drones, that's significant. But these drones are being used. These unmanned vehicles are being used in many different ways now, and Ethernet is viable in many different solutions. So yeah.
I mean, it's not. It's just UDP IP. It's as simple as it gets. It's at the protocol level. So. And it's statically configured, so you don't really need to have like a full, TCP/IP stack with ports and all of that stuff. It wouldn't be. I can't imagine it's any more complicated than Mavlink at the end of the day at the code level. So,
but go big or go home.
Yeah.
Why have one stack when you can have them all?
But you could technically then hook up a ring laser gyro to an ArduPilot flight controller or something like that, which sounds outrageous, but maybe down the road that's the sort of thing people would want to look at doing.
Yeah, and there are cameras and sensors and stuff that are Ethernet only, just right. Because the sheer massive amount of data that they generate.
Right. Yeah. I mean, it'd be really great as a protocol for daughter, for companion computers, that sort of thing.
Yeah, and that's been the argument too. Is the right tool for the job, right? Is the autopilot itself the one you want to be feeding hundreds of megabits of LiDAR data to? Or is that some sort of Linux computer that's got gigs of RAM that can handle all that?
Well, it's a multiplex bus, so you could have lots of peripherals talking on that bus, including companion computers running flight software, and included on that bus would be the flight controller that needs to also get data or send data to those peripherals. So
yeah, there's definitely a use case for it.
Just when I see you using CAN to do that, and then that's also something that's done on large aircraft, of course, as a field bus technology, but that's heading in that direction where you've got multiple peripherals on a multiplex bus and lots of data moving around. And it's not outrageous to think that pretty soon people will want that sort of bandwidth, for video data and all sorts of things. Yep. All low latency, perhaps, is the other thing to consider.
Yep, indeed.
Anyway, I just seemed like the right place to throw that out there.
Yeah, thank you. Anything else? Is there anything on the YouTube channel or stream?
I'll just go and check it now to see if there's any questions that turned up on the YouTube channel. If somebody else has already been following it. And apologies to those on the YouTube channel if we haven't been tracking things properly. And just a second, I am checking it now. And yeah, it doesn't look like to be anything about the AP Proof talk. So I think we just need to thank Tom very much for his talk this morning, and greatly appreciate you putting that together. And that was very short notice. Tom was only knew he was giving a talk a couple of days ago, and so very short notice to put this together. So we've got a little bit of extra time now, and I'll just stop the recording on Tom's talk. So we've got a little bit of extra time now before we're scheduled to start the next talk. I think we should at least have a bit of a break to allow people to sort of stretch their legs and and maybe make a cup of tea and have a toilet break. How long should we do that for before we start back? The next session is on documentation. So we've got Henry leading a discussion about the 4.1 documentation, or documentation in general. The focus really is on how prepared we are for 4.1. And so this will be a different type of talk. There'll be a lot more interaction between the dev team members, and in particular, trying to work out who's going to put their hand up for, documenting some of the pieces that aren't yet documented. So I'd suggest we maybe start up, say, quarter to the hour. So that would be in about 9 minutes from now. What do people think about that?
Yeah, I think that's good.
Yep. So about 9 minutes time. So we'll leave the call open. And so feel free to chat among yourselves, and then we'll get a cup of tea, stretch our legs, have a toilet break, get back in about 9 or 10 minutes time, and we'll start off on the documentation discussion. Are you all ready to go for that, Henry?
Yep.
Fantastic. Thanks, Henry. Okay. Talk to you all soon. And it is still being recorded, so it's still on the live stream. So no private discussions while we're having our break.
Oh, that's creepy.
No, it's not.
It's weird.
What's creepy?
Just you.
Yeah, thank you, Tom.
He sort of opened a door in the field and walked in. It was like science fiction movie or something.
Oh,
Yeah,
I
you-
see. Yeah,
you
yeah,
wa-
did
you
some
walked out of
really-
that
really odd effects with this video background.
Yeah.
I could
Sorry, I was
switch
just-
my other background while I'm on, on the break here.
I didn't mean to call you weird looking, but just call it like I see it.
I'm having my favorite snack, which is cherry tomatoes. Mm. Yeah, the ESC stuff I think will be really interesting. We'll have to get nice test benches set up to test it out. We should probably also talk to the VESC project, because the VSC code is really nicely developed, as Leonard said. The main issue with it is turning it into a library, because it's really not structured to be made as a library. And how would we bring it in? Do we just fork it completely, in which case we lose the advantage of its further developments, or it's very hard to keep, to merge further developments? Do we do it as a submodule and try and use some WAF tricks to bring in pieces of it? It's a bit sort of tricky how to incorporate it. And it might be worth having a discussion with some of the VSC developers to see if they've got some ideas. At the moment, I'd be inclined to do it as a bit like we did Shibios, which is, so Shibios has got its own build system, makefile based, but then Sid came up with a clever idea that uses basically WAF to enable us to build Shibios as a library. And we could possibly do something similar with the VESC, with fairly minimal patches to VSC on top of their main repo, and bring it in as a library.
Have you come across ODrive?
No, I looked up ODrive when you mentioned it just a minute ago, Pete, and I ended up, I'm not sure I went to the right site, because, so I looked up ODrive ESC, and it's odriverobotics.com. Is that it?
That's about right. I think I just posted a link to the GitHub.
Okay, where's a link to where did you post it?
Oh, in the Zoom chat.
In the Zoom chat. All right, let's have a look on that Zoom chat.
Yeah, that's another one that people have had a lot of success with.
Yeah, I've just been playing with one for a rover project, and it's quite good fun.
Now, ODrive sounds like Open Motor Drive. Those are like totally unrelated, right?
Yeah.
John didn't.
Yeah, Open Motor Drive was the one that led
Yeah, that
by
John did from
Challenger.
scratch and all that. Yeah.
Yeah, both the VSC and the ODrive have both been around for a while. They're both mature. They're both pretty fully featured. I've had some VSCs here we used on some skateboards, and they were quite powerful and easy to tune. They did what they
Yeah.
intended.
I just got one of the VESCs set up on one of our rovers. We have 6 motors. We just pulled Nick's truck with it a few minutes ago.
Yeah, if anything, I was hoping that we could use the VESC hardware as the base, right? Because you get a free ESC on it.
Well, it's interesting. So I think for it to be really successful, we ideally want it to be able to run on really low end hardware, a bit like the BLHEL32 can, because that gives much wider adoption. A much larger part of our community could use it. If we only target the higher end, so the small subset of our community that want the really high end ESCs, then we won't get as wide a test community, which really helps push the development of it.
BLHEL's recently had an open source version of it made.
Yeah, the AM32. That's what I was thinking of.
He's been working on it for a couple of years and it's only just sort of come out of the closet with it.
Yeah. I had a look through the AM32 code a couple of days ago, and it looks fairly easy to understand. It doesn't do FOC, although he recorded an interview where he said he's considering adding FOC support. He's looking at it. So he's been going down the path for sort of reproducing BLHL32 features. And as a baseline, it looks quite attractive. But so we've sort of got these different paths to go down. Sort of VESC has the FOC stuff, and the key thing is, how easy it is to incorporate it. I don't think we are likely to run on the low-end BLHL32 ESCs, the F0 ones, because the AP periph just would never run on those, just not nearly enough flash. So it would only be sort of the F3 and above type ones would be interested in targeting anyway. So maybe we can just knock off the ones targeting the really low end ones, because it just cramming it down into such a small flash footprint was just far more work than it's really worth.
This ODrive is an F405.
Okay. Well, that's an easy one.
Can pins on it.
Yep.
I can. I'll wave it about here. So that's it there. And this is the motor I've been messing with, which is a wheel off one of those children's hoverboard things. But it's very powerful. Nearly twisted my arm off when I thought, I'll just see how powerful that is.
Yeah, I wish I could show you the videos we took today.
Yeah, some of the brushless motor power tools that are coming out now have thrown a few people off ladders, which is not fun if you're the victim, but quite hilarious if you're watching the video. I actually have one of the drills that I bought for rewiring part of the house has a torque sensor or a clutch in it. I'm not sure which it is, but it's specifically designed because the predecessor to that tool had a reputation for taking people, throwing off the ladder, and usually breaking a wrist in the process.
That's a nice photo, Henry.
Oh, yeah, somebody was chasing me. That was about 7 years ago, I guess.
Mm-hmm.
So when we start mine, I need to click the share screen button, right?
Indeed, and I think we've had our break now. So so I'm just going to start the recording for the next session.
But I'm prevented from screen sharing.
I will fix that for you right now. So just hang on a second while I go and fix that. All right, so welcome back, everyone. And we now have a session on the ArduPilot documentation led by Henry, who's been our documentation lead for a few years now, and really concentrating on preparing us for the 4.1 releases and making sure we get all the documentation right. So over to you, Henry.
Okay, thank you. Just a quick update. In the last year, we've had about 1,100 commits to the wiki. Not all of them spelling and punctuation, most of them substantive. The logging page has been expanded, thanks to Peter, with detailed explanations of the logs. We don't have any build errors in the wiki. I do a daily check build and fix anything that pops up, usually within a day or so. We've added to the wiki an upcoming feature sections to contend with master only code changes and features. Pending PRs are mostly for 4.1 and are actually already in the wiki, either directly or by reference well, the PRs would be by reference via the upcoming features page. PRs are addressed in a more timely fashion now, and usually get to them within a day or so if they come externally. Open issues, we're running about 110. They get reviewed by me bi-weekly. A lot of them are unresolvable at the present time. Things like multi-language support, wanting to have the wiki generated into a single PDF file every day, things of that nature. But we try to keep those number of issues down to a reasonable level. Handling of features not unstable. We took on a different methodology this year. Previously, dev branch or master branch only additions were tagged with something in the wiki when they were added into the wiki as only in firmware version X.X. This leads to a pretty nasty maintenance issue on how to find and retire all those comments as they become out of date. So we instituted a new system this year where the wiki main reflects stable. Whatever stable is, we keep it updated. Master only editions are included in a section in every vehicle called upcoming features, which will list all the new pages for like what 4.1 will be now. And there's a subpage in there for other like one line or paragraph line changes to parameters or functionality or things like that called other wiki changes. This hopefully will allow when we actually do a release of 4.1, cut and paste into the main wiki just directly without having to hunt around and remove old taglines or figure out where old sections have to be removed. 4.1 release. I estimate probably, I don't know, 80% of the wiki already exists in the upcoming features. I've been tracking everything every day that we add as a commit that should have a wiki addition to it, and either putting it on a issues list, which we'll go through momentarily, or actually creating the wiki entry under upcoming features. But there are still some significant sections remain. Like I said, there's a standing wiki issue. If you go to the wiki and click issues, there's a pinned first issue, which tracks every added or changed feature or function added to master as best as I can keep up with them on a daily basis by watching the GitHub activity. And an assignment currently is based to who coded it, but only when I don't understand enough to do the wiki additions myself or just don't have the bandwidth. So at this point, this is what it looks like. It's issues 1756, but you don't have to look for it. If you go to the wiki's issues page, it's pinned hard up at the top. And this will also, as we go through this, give you an idea of the massive amount of features and additions that have gone on between 4.0 and 4.1. It's really amazing. So I can't put the list on a single page, of course, so we'll just click through them. Now it'll give you a chance to look through them as a event. Where there's a checkbox means it's already been added into the upcoming features page by one method or another. And then there are numerous open boxes. Really big is a lot of the bendy ruler and object avoidance stuff, a lot of the new protocols for CRSF and things of that nature. But a lot of things we've covered. A lot of things like the plane now has fences like copter. So we have a lot of wiki work that needs to be done on that. Things like wing sail, winch changes. Then we started getting into sections where I haven't been able to update it or hoping that the original author will actually do it. When it comes to these things, you don't have to create the entire wiki. I can put all the words and formatting and window dressing around it. I just need a bullet list of features and important functions, enough information to explain the operation, and it doesn't have to have a lot of words with it. It just has to have a lot of content. So bullet lists and things like that, and I can help with the work. But where things are that I haven't been able to or don't have the knowledge base for, I've assigned to the original code author. Where things where I could figure it out, like air brakes or the new soaring function switches, whatever, I could already add it into, or have already added them into the upcoming features. ICE start channel, PID slew rate limiting, the new DMOD stuff. Oops, there we go. The wind parameter and wind warning parameters, things of that nature, memory guard, but a lot of the stuff has already been added. Disk theory, pivot turns, excuse me, battery monitor, run cam control. I don't even think this high-tech CAN GPS is available yet, so that's not really an open issue, but there was WIP for it. Smart RTL, so forth and so on. The list goes on and on. 4.1 is huge. A lot of the things I've got open action items on, and I knock a couple of them off every day, where I can have enough confidence in the knowledge base to create the wiki for it. I'll try to alleviate the burden for the coders for that, where it's not really need help in that area. Another page, more empty blocks. And the final page. So you can get a feel from that we have just a huge amount of features, additions, changes. Luckily, a good deal of it has already been done, but there's a good deal that still needs to be created. And every day we add some more. Anybody have any questions about that or anything that I've talked about so far?
Just a comment. This is really impressive that they actually show that you can get this list like this from pull request and itemize it, so you keep things without, don't let anything slip through the cracks. This is quite nice. Good job.
Thanks. Well, it just, you got to watch the GitHub releases every day.
Yeah, there's a few other sort of bigger items as well that aren't captured. The new ground station work from the donation from Intel, which we're going to have a talk on tomorrow. That one, it's got its own set of HTML documentation, and it'll probably end up being a separate wiki. We'll just need to, most of the effort would be on import tools to sort of get that translated across into a format that fits in with the rest of the ArduPilot wiki. And that'll be worth discussing with the with Marco and others from that group. For the rest, I mean, most of it, as you say, we just need sort of the dot point description, to be able to start it, even if we get minimal information. I don't think you've got the, because it isn't merged yet into master, the new plain PID system and auto tune. That's definitely worth linking in there, because that'll be a fairly major one that's really important for the plain 4.1 release, because it completely changes how people tune their fixed wing aircraft. But the great thing is that you're getting very familiar with that because you're doing a lot of the testing of that feature. So it should be, much easier to work with you to make sure we document that correctly.
Right. Yeah. If it isn't in master, it's not on this list.
Yeah.
So, that also leads into some other stuff on the next slide when we're through questions up to this point.
Yeah, we should, the dev wiki, I didn't see the thing there, but the different, the @sys file system and that sort of thing. So the various AP file system, we should at least reference the list of those and what they're for in the dev wiki, if we haven't already. So I think some of those have snuck into master as part of other PRs without them getting open issues for the dev wiki. So if you remember in my talk yesterday, I talked about the expansion of the sys file system. And similarly with the new mission file system, there's a pending PR for that. It's worth at least referencing whether we actually put the protocol documentation that explains the format in the wiki, or whether we're better just linking people to the code, because I've put a block comment in the code describing the format of each file. It might be better to actually just do that instead of duplicating that information, because the dev wiki is aimed at programmers, so presumably they're not afraid to read a bit of C++ as long as they've got a link to it so they know where to find it.
No problem. We can add that on the AP file sys as a bullet on here.
Yeah,
somebody needs to write up.
Yeah.
Some of the things we did add, right? Recently we added the embedding of params and scripts and stuff like that. So that's already in the upcoming, or perhaps even already in the standard dev wiki, I think. I forget, but it's already in the wiki someplace.
I feel like this could be automated somehow, because we have hooks already for Discord and other things where you have hooks to look at the events on GitHub. So if anything gets merged, you can be like suck it into an RSS feed or something.
Well, we originally had wiki needed, and we've been pretty good on that. Or if I see one slip past, I try to tag it with that. And then every 2 weeks I go through and look at the wiki needed and make sure they come onto this list in case I've missed it overnight or just haven't recognized it, because there's several days where there'll be 60 commits on the GitHub activity, and running through the titles, I may miss that one is important to have a wiki associated with it when it doesn't already have the label appended to it. Yeah, if we were a little more rigorous on making sure that wiki needed labels were put on the PR as it gets merged or before it gets merged, then it'd make it easier for me to make sure that this list is accurate. I think it's pretty accurate. I don't speak up anybody that's didn't see anything on the list as you review it or whatever that we need to put in there. Please just drop me a note and we'll look at the PR. I mean, look at the commit and go from there. But the biggest issue is all these blank boxes.
Yeah, that's right. We need to start filling those in.
You don't need to fill the ones that have HW on it. I'll figure that out. The ones that don't have my name on.
Oh, I actually thought HW was hardware. Yep. So the other one is, I think it's worth for 4.1 reviewing our sort of architectural diagrams for ArduPilot, because particularly like the control flow diagrams, like the ones that Leonard has done for his control has been really good. And I think those high level control diagrams done in the sort of the standard controller forms are really valuable, particularly when you're interfacing with research groups and showing exactly how, the cascaded PID architecture works and where the various pieces fit together. And some of those are getting a bit long in the tooth. I know Leonard's been doing some updates on his. What's the status of getting sort of an updated control flow, architecture diagram in Leonard with all of the changes that have been happening recently? Are you there, Leonard? Or have we lost you? So Paul as well, if you, it'd be quite nice to work with you, Paul, on getting a more accurate one for fixed wing, the overall control architecture. So and sort of review the existing ones that are there for techs and the fixed wing control, and then just check that they're still all accurate for 4.1, because there's been so many changes, particularly in filtering.
Yep, no, Andrew, it's Paul.
Yep. Hi, Paul. I see you're having a snack. Sorry for interrupting your morning tea.
Yeah, no, that's okay. So I was just thinking about, I had a look at the previous diagrams were generated, essentially the very original modeling work was actually done in MATLAB Simulink years ago.
And it can generate diagrams, can't it?
Yeah, that's right. Now, I don't use Simulink, don't have a license currently, but they were pretty simple diagrams. So I can just throw them together using, I don't know, some open source tool that means that they can be maintained longer term if we make changes to them. Because I think,
yeah, that'd be really good. It'd be nice to decide what tool we're going to use for those sort of control diagrams. Needs to run, on Windows and Linux preferably, and save to a format that we can update. That'd be great, because I think, I think those control diagrams, it's fantastic to be able to point, when you're dealing with research groups, to be able to point them at an accurate description of exactly how data flows through, how the control works.
Yeah, so I mean, I haven't really looked at what tools would be available or would be suitable, but if there's anyone on the call that's had experience with a tool that's been around for a bit, obviously not something that's shiny and new and might disappear in 12 months, but something that's got a little bit of pedigree to it, then I'm happy to regenerate the diagrams for that.
Yeah, so I think we'd want the fixed wing control, we want probably text, and maybe L1. Is L1 worth doing, Paul, as well?
I think it probably is. I mean, what's there at the moment is probably more, not so much a block diagram, it's more of a graphical description of the underlying concept behind the algorithm. But an actual, I think a diagram would be useful because it would show us where does the integrator term fit in.
Yeah, it might need to be two diagrams, because it actually varies a fair bit depending on whether it's locking into a circle or whether it's navigating a path.
That's correct. Yes. And
I would love documentation just so I can find that crosstrack bug.
Yeah, well, I was looking at that issue just the other day, and we've got an integrator in there, which in theory should wind that out. So that's got me perplexed, but that's another topic.
I added that after talking to you about that. So that's the weird part.
Yeah.
Okay.
Okay, moving on. So some topics for discussion. Need assistance in documenting 4.1 and future releases. It's real tempting to code and never document, I know, but the job's not over till the paperwork's done. The real problem is nobody else can use it, your brilliant idea, unless it's written up. A couple of things that I have would like to discuss is I would really like to see, I'm a tail sitter guy, got 5 or 6 conversions, tail sitting tuning guidance, which is unique because most of them are vectored and don't lend themselves to any auto tune very well. Maybe the roll axis, if you're lucky. The real problem is that with a normal stance vehicle, you can pick it up off the ground, do some tuning, put that back down, and not crash it. Unfortunately, with tail sitters and TVBSs in particular, VTOL's tuning is extremely difficult. At least I found. We have no guidance whatsoever. And it's potentially costly in terms of breakage coming up and down. So one of the things that might help that is another thing that, as I've gone through trying to learn how to tune these things, we have a lot of log information provided with all the PIDX information and the attitude information graphs. I may be totally screwed up, but it would seem to me from that information after your first flights, even if you're doing the VTOL stance in air and not from ground, that you should be able to get some information about directions for tuning, or at least be able to give some extreme cases of here's where you've got too much or too little D, whatever. And I have enough control background with my master's just to be ignorant and dangerous in that area. And I think it'd be really worthwhile if we could provide some guidance from some of the good logs that we now produce. I may be totally off the wall on that, but open discussion on those two things.
Yeah, it's a very good example, that vector tail setter tuning, and it's one that we've of course got two efforts underway at the moment to create new auto tunes. There's the helicopter one that Bill is doing, and there's the fixed wing auto tune that Paul and myself and yourself, Henry, are working on. And I think there are a bunch of ideas from both of those that may be applicable to the tail setter tuning, particularly though the slew limiter detection to detect whether you've gone over the top on your P or D. That seems to be panning out really quite well in the fixed wing tuning. And what do you think, Paul? Do you think that might be applicable to, for example, the pitch axis on a TVBS?
Oh, look, totally. I mean, the key there is a reliable detector of the limit cycle, and a measure of either the peak or the RMS slew rate generated by it, an amplitude. So if you've got the peak amplitude and the peak slew rate, like peak to peak on the amplitude and peak to peak on the slew rate, then that gives you really good information about setting bounds on those, and then winding the gain up and down. So you can detect that point where you start to run out of phase margin. So I think what you and I need to do is actually work on making that slew rate detector, or it's really a limit cycle detector, making that more reliable, so it spits out not just the rate of change, but also the peak to peak of the displacement and the peak to peak of the velocity.
Yes, I think if getting that as like a core library that's really reliable, and then I think it'd be very worthwhile to start applying that in the tail setters. And the tail setters is one of our more challenging ones to tune. If we can, I mean, I think I completely agree with Henry. Providing good documentation on guidance on how to do things manually is really important. But even better if we can provide tools that make it easier to do the job. The
TVBS challenge, I found after 6 conversions from wings to conventional cargo carrying aircraft, is the yaw axis. Mm-hmm. That's the one that is the hardest to get locked in for me, and no rhyme or reason on how to do it. Yaw axis earth frame when vertical. Roll axis body frame. Yeah. I'm sorry.
So differential tilt on motors when the nose is pointing up.
Differential tilt on motors. Yeah.
Right. Usually the defaults, and I've done a wide range of from small to large, meter, more conventional planes, twin motor TVBSs, and Pete probably has done a lot more in sim. Yeah. But
there's an underlying issue there, which we probably want to cover on a tuning guide, and that is that if the center of mass of your motor assembly is in front of the pivot axis, then you get when you tilt the motors differentially, there's an inertial reaction torque, and the initial response of the vehicle, angular acceleration and velocity, is the wrong direction.
Yeah.
Right. It's what's known as a non-minimum phase system in control, and that's got some specific tuning challenges and some traditional workons as well. So we can have a talk about that.
It's a bit like the tail, on fixed wing rolling takeoff when you have the canted wheel at the back. Yeah, you get a similar effect.
So, yeah, so pitch and roll with defaults usually is kind of flyable right out the bat. Yaw is not good enough to do a loiter with, and until you can do a loiter, you can't really do VTOL auto landings and stuff like that. So anyway, yeah, a good tuning guide for tail sitters is, I think, one of the things hindering its acceptance. I'm personally a TVBS advocate as being one of the most efficient VTOL platforms. But anyway, so, and I think along those lines, it might be good is it possible, I'll ask this of Paul, is it possible by looking at the logs generated from a normal, a flight in vertical, to get some idea of directions to move things? Not talking about getting I'm talking qualitative versus quantitative.
Yes. Okay. So feed forward. I don't know if we've got feed forward. We have feed forward on all of our loops now, I think. So that's a bit of a no-brainer to get from a log, in terms of, you know, how much actuation gives you how much steady state rate. And then the other thing you can pull out is the angular acceleration produced. The challenge, though, where you can't do a simple direct graphical analysis, is, as I've said, depending on the layout of the system, is that non-minimum phase behavior. And my recommendation there is, I don't think our controllers are currently set up to really handle that properly. I mean, the recommendation is really that people construct the vehicle, probably get the pivot point for those motors as close as possible to the center of mass of the motor. So, which makes the nacelle a bit bulkier, obviously. Yeah, we could pick that, and if you do that, then you can pick up the relationship between tilt and angular acceleration.
You're talking about the motor mass pivot point,
yeah,
not the vehicle mass. Okay.
No, the motor mass pivot point. So all the bit that's the motor assembly. If you pivot it around the center of mass of that, let's put up with the extra frontal area. Makes it a bit bulkier, but it's going to make it a lot easier to tune. Otherwise, you're into some slightly more control theory.
Yeah, that's something I kind of follow anyway. That's good mechanical because it reduces the amount of servo power you need to move the motor in the pivot if you have it.
That's right.
So that's something I've done intrinsically. But anyway, that's get off that. So I think that's an area that could be done. Okay, so another thing that I want to discuss is we had some actions from last year still unaddressed. One was mission commands proofing. We actually had, I think, somebody volunteer for that, but we never got around to it. Where we have lists, it's a pretty clumsy.
If I could jump in on that one, Henry. Yes, that was me that volunteered, and I am working through that as we speak. So I'm going to put a PR in the next couple of days, which will have basically back-checked everything compared to master and added in the new one. So it won't necessarily be formatted. It won't necessarily be formatted correctly, but because I think you've had you've got a bit of a vision as to how you want to have that formatted, but it will certainly be factually correct.
Oh, super. Yeah, super. Great. Thanks, Matt. I really appreciate it, because what I want to do is get it so that it's correct, and then make sure then we can have a discussion on whether we want to keep splitting things out like Copter did from the master list or not as a separate discussion. But right now there is a master list that has a bunch of defs on it to make it each section or each command, mission command, differentiated by vehicle. I think Copter broke out a set independently, which I don't think is up to date either. But in any case, getting the master list all proofed would be the first step, and then deciding where we want to go on that. And as going through that, by the way, we found a couple of I ran across myself a couple of mistakes that we had to correct on the behavior of some of those commands. So it's a good exercise. Last year, we also talked about making camera and gimbal better, and in terms of getting it accurate, up to date, and in a better structure. And I don't have a lot of experience with gimbals per se, but so that one hasn't been addressed. And then open to any other improvements anybody has to the structure of the wiki. We went through, one of the first things I did when I came on board 1.5 years ago or so was try to get it structurally more consistent between vehicles and in a flow by where somebody new, because I come from the hobby sector, new to ArduPilot, can get something up and running pretty quickly. And if you just go through first setup and first flight, you're pretty much assured to be in the air and get all the information you need. And then everything else is kind of window dressing for the vehicles. So, and then anything else, Andrew had a couple of things that I've noted as to things we should be doing. So at that point, I'll let it open to any issues or questions.
Thanks, Henry. Yeah, it's so great that we've got so much of the documentation already prepared for 4.1, and we just need to make sure that we fill in those gaps. Need reminders from Henry to make sure we go and write the bits of documentation, because as Henry says, unless we actually document it properly, then the ability for our users to take advantage of the new features is really somewhat limited. It's, as a developer, it's a lot more fun to write the code than the docs quite often. And so we need to resist the temptation just to add, just to keep adding new features and not go back and document the existing ones.
And again, you don't have to make a wiki. All you have to do is give a bullet list, and believe me, if I have questions and don't understand how things work, you'll get questions back on it. But I can get the work done for the majority of the stuff. Of course, I don't have but a few hours every day, but any help is always appreciated, and a lot of you guys really do keep up when you add a feature to adding stuff, and that's really a help. Just need everybody to do it.
One that came out of the last talk was Tom pointing out that we've been really slack about the parameter documentation for APPref, because we haven't been filling in the documentation comments for the auto-generated parameter docs. And I do think we should go back and start filling those in. And the same with CITL. At the moment, all of our CITL parameters, we don't have the param docs for those. And there's a significant task to go through and fill in all those parameter doc comments in the C++ source code, so that we can auto-generate the sim parameter documentation, so that it's available in the ground station.
But I don't.
Relevant to this, I actually merged into master the tooling to actually do that.
Okay,
so
thanks, Peter.
We now have a --CITL option to the relevant parampars.py, which will generate something that's suitable for inclusion in the wiki. And I'm pretty sure I spotted a patch from Randy, I think, that added documentation to some of those, or no, that was actually just adding comments, not documentation, unfortunately.
So do we have? You'll have to work with me, Peter, on where we can get that wedged into the wiki.
Yeah, it might be better going into the dev wiki rather than into the main vehicle wiki, but yeah,
it should be part of the CITL portion of the dev wiki.
But it also needs to be in the ground stations. So the automatic documentation download that happens in our ground stations that gets sourced from those parameter comments, I think we should populate that. So when somebody's using, for example, Mission Planner to do CITL, and they go to the sim parameters, that they actually get the documentation for those parameters filled in, which means we do have to include it in the XML file we generate, even if we don't put it into the wiki, into the main, vehicle wiki. So there'll probably be a little bit more tooling work to be done to make sure that all gets plumbed together.
So you mean if I just hook up to a normal plane with Mission Planner, I'll see all the sim params?
No,
too?
you won't, because the ground stations already exclude any parameter that they don't see in the download of the parameters from the vehicle, right? So, for example, if you connect to your Omnibus F4 Pro, you don't see a lot of the BRD parameters that are specific to boards with an IOMCU. They automatically get excluded. So our XML file that we give to the ground stations and gets downloaded from the firmware site can include parameters that aren't actually on every vehicle, and that can include all of the sim parameters. It will mean a slightly larger download of that XML file, but I don't think that's really significant.
Actually, I'm generating a separate file for the settle parameters.
Right, but that'll mean a bit more tooling, make changes to the ground station. Why don't we just include it in the same XML file?
Well, the problem is we lost my initial shape for this was to add an @hal thing, which would have kind of permitted that, because we could have plumbed that through, so you only saw the sim parameters in SITL. You don't want to mix these in with.
But you won't see them anyway, because the sim parameters won't turn up on the ground station. So ground stations automatically exclude the parameters that they don't see.
Pretty sure some of these things actually have kind of offline modes where I think QGC, you can get a parameter list without connection to the vehicle or something along those lines.
Okay. Seems like it would, like a one-line thing to QGC to exclude the sim parameters if it's not SITL, I guess. But I just want to make sure that it does turn up in the ground stations, particularly in Mission Planner. And I've found it really valuable to be able to point new users at the SITL experience within Mission Planner, the button to launch SITL, and then configuring the vehicle. And those sim parameters should be part of that.
So initially, I wanted something in that we could actually start getting value out of the markup that we would add to the code.
Sure.
So I was happy to get anything in at this point. And at the moment, I only generate the RST, not the XML. So
right, okay, yeah. No, I mean, you're right. It's great to have a start. The end goal should be that the ground stations do have it, and you should be able to do param help in MAV proxy, for example, on any sim parameter.
Yep, but chicken and egg, and I wanted to actually break that.
Yeah, I understand. It's a fairly large lump of work to document all of those parameters, and they tend to change fairly quickly, those params. But I think it's similar to the AP perif. We need the AP perif ones and the sim ones. We've just left those out of the automatic generated documentation so far, and that should be one of our goals this year, to ensure that both of those are fully filled in. Yeah. The other one that's worth reviewing is some of the units. Well, you got those PID ones up on the screen there, Henry. We're not entirely consistent in our units on the different messages. And I think it would be nice to, for example, standardize on, either degrees per second or radians per second on all of our rate messages. And personally, I'd prefer degrees per second. I know a lot of the control people would prefer radians per second, but I think degrees per second is easier to understand for most of our end users. Sorry, Leonard?
I agree.
Hey, great. I got you on board. Excellent.
Degrees per second in the parameters, radians per second in the code.
Yeah, and the radians per second in the code I completely agree with. But the log messages are an interface to users who are trying to tune. It should roughly match. It should match our parameters. And so I'm even thinking of saying that for example, the IMU message is currently all radians per second. It would be nicer if that was degrees per second. So yeah, anyway, that's something that I think is worth looking at, but particularly the PID ones, to understand the units of those and make those consistent. It will be easier with the switch of plane to AC PID, so at least we're using a common PID architecture.
The PIDs are a little bit trickier, Tridge, because the PIDs themselves are unitless.
Yeah.
And so we would need to have some sort of parameter or some sort of definition with the AC PID to say what unit that was actually in.
Yeah. Yeah.
So if we did that, then we could actually set the PID log to be whatever the unit is. We've set that PID that's operating. So it would be meters per second for the Excel, meters per second for velocity, degrees per second for the rate loop. You know what I mean?
Yeah. Yeah. At the moment, even the AC PID plane patch treats it scales the PIDs so that they're in our pseudo degrees, minus 45 to plus 45, which is our like surface deflection. I think it's worth considering whether that's the right choice.
No.
Yeah.
That's a hangover from back in the days where we never had floating point numbers.
It's done as a float. It's 45. It's not 4,500. It's done as a.
No, but that's the thing. 45 is just meaningless because you don't have 45 degrees of deflection. It's just some random number.
Yeah.
Yeah, it is. Right. It's just a completely random number. And that's why we use plus or minus 1. And it's a normalized output that's full deflection. You could say percentage, but plus or minus 1 is pretty much percentage, but plus or minus 45 degrees or 4,500 or whatever other random variable you choose there is it's just like I personally think we should be moving all of the servo outputs to plus or minus 1, not plus or minus 45 or 4,500 or something like some other random number.
So, yeah, I've got to make Mav Explorer a bit smarter about the unit handling. We've got the nice unit messages in our logs now, but Mav Explorer doesn't really take advantage of them properly or at all, really. So that's something that's a to-do for myself and maybe Peter if he's inspired.
Yeah, I have a branch for it somewhere.
Okay, great.
Which actually adds it so you get your axes labeled appropriately.
Right. Okay.
I think there's actually code in there so that it changes things from things like radians into degrees if they're not already in your preferred units.
Yep. All good. All right. So what else do we want to discuss around documentation at the moment? Did everyone note where their name was against items and put their hand up? Everyone promised sincerely they'll work harder on documentation?
Yep, for sure. I just stuck actually Leonard's latest attitude control PID diagram at the top of the copter attitude control wiki page. Just a small
All right.
thing.
Okay. So where did you put that? I can't.
Right at the top of the page. It might take it a minute or two.
Oh, you put it into the wiki. So. Right. Okay. Great.
It's this page here. I'll just put the page in the chat there, but.
Great. Okay. All good. Okay. So if we're done with the documentation, we can move on to the next talk. And Rob has already let me know that that he's available to start his talk a little bit early. Is that correct, Rob? So you're there now? Rob, hello. No, he pinged me just a few minutes ago. Say that he was available to start a little bit earlier, just to see if he's actually in the list of participants here at the moment. He seems to have dropped off. All right, so we might just wait. We might have a few-minute break. I know he's available. I suspect he's had another call or something that he's had to attend to. So we might just take a few-minute break. So it's say we come back in and see whether he's ready in say 5 minutes time, or should we make it the quarter to the hour? So 11:45 Canberra time, say 8 minutes.
Yeah.
All right, let's try and make it back here at the 1:45, and hopefully Rob will be ready then, and then we can move on to the ANU visual odometry system.
Hey, Tridge, so I captured a number of request action items. How do we want to, where do we want to place those?
Sorry, Henry, I was just
I'm back.
Rob.
I was just in the other office.
Right, no worries at all. So we decided we'll start in about 8 minutes time, so at 1:45. Is that okay, Rob? And your camera is showing a nice view of the ceiling at the moment. Is that deliberate to be having a view of the ceiling, Rob? Okay, I recognize that was Rob. You're muted, Rob.
Well, it can't be. Oh, well, I just said something.
Yeah, am I right?
No, he then muted himself. Yeah, he's now unmuted again. We are getting odd views of your hands flashing past. That's better. That's much better. Excellent. Okay, so we're starting in 7 minutes. So 1:45, we're just having a few minute break, and then we'll be starting up.
So Tridge, I captured a number of action items in that discussion. How do you want them memorialized?
So I'm not quite sure. I'm just helping. We've got another speaker from tomorrow who's asking me for help how to get on the Zoom. So I'm just going to help her out getting on the Zoom.
Just a suggestion, Henry, is do it the same way that Copter does its blocker lists for its releases. So basically an issue with checkboxes in it.
Well, I can just make a separate section under the master list that I keep, if that's acceptable. Comments?
Hey. Yeah, if the other, you could do things like create, if they're assignable to specific people, you create an issue per thing and assign it to that person, and then keep then link to that issue in your master list.
Okay, I can do that. I'll create wiki issues like that.
Hey, Henry, you mentioned, was that tongue-in-cheek or were you serious earlier in the presentation? You were saying, you talked about generating a PDF every day. Is there demand for that, or was it just tongue-in-cheek?
There have been at least 2 requests over the last year for people that want to have an offline copy of the wiki.
Okay, so I guess that's not that much, because it's fairly easy to do with the current setup that we have in Sphinx.
Yeah, we should be able to automate that.
HTML, you just generate a PDF. I've done it before. I can't remember if it's plugin, or I think it may come straight with the version of the Sphinx.
It might be worthwhile doing that and having it just up on our firmware server. It shouldn't be anything that Henry needs to work on. We should be able to just update the scripts and automate it and generate separate PDF for each vehicle type. So a copter PDF and a plane and rover and antenna tracker and blimp, etc., as separate PDFs.
The only bug in the fly in the ointment on that is the params versioning, perhaps.
Yes, we would need to do pick one of the parameter versions and lock that in, because the dynamic parameter version selection just wouldn't make any sense in a PDF.
I would suggest stable, but
yeah, I think you're right. whatever stable is for the current vehicle, because this is sort of a reference guide you take out to the field when you have no internet access. I think that'd be very worthwhile. We could also have it as a HTML zip file, which a browser could open, and that might be just as useful, and that would allow the JavaScript to run potentially, depending on your browser, whether you can run local JavaScript. But whether it's better off as like an HTML zip or a PDF. I mean, PDFs are more familiar to people, but less flexible.
So,
yeah,
Olivier,
navigate.
Olivier, is that something you wanted to do?
I've actually done it, but I think it's been like a year or two. I put an example of a generated thing somewhere on GitHub, but yeah, I could definitely look into this.
Cool.
I think I hadn't thought about this, but the HTML zip is also pretty nice, because the navigation then, I mean, you're just exactly the same as except for the parameters, you're just exactly the same as if you were online. So maybe both of these things. And as Tridge was saying, it's just one more cycle in the build. It shouldn't be a big deal.
Cool. Sounds like you signed up. Super.
Hey Tridge, on that PID logging thing, I should turn my video on when I talk so people can actually see when I'm smiling rather than not getting too serious. How hard would it be for us to actually, I'm not sure. I imagine that the overhead of actually defining the units of a PID shouldn't be too hard to do, right?
Yeah, that's right. We need to make sure the log messages sort of reflect the units, because we do have those the units in the unit messages, so that all log messages have units on all the fields.
And the other thing is too, like we can say something's radians or degrees or something like that.
Yeah, we can.
log.
That's right, on the log messages. Yes.
Yeah. Now, does it is easier when you can sort of see just the raw data as the in degrees over radians. But does Mission Planner, I think, converts a lot of that to its sort of default display units, right?
We've reached the start point. We might discuss that a bit later if you don't mind, Leonard, and we'll move on to Rob's talk.
Yeah,
that's okay. It's a very interesting discussion. We just might do it a little bit later.
I lost track of that time.
So thanks, Leonard. All right, so I'll just start the recording here. I don't see Peter on the call yet, Rob.
No, so we had some computer problems, which we saw. He was going to be in the room with me, but he sorted himself out onto another computer, and he'll have to present his half of the talk there, if that's okay with you.
Right. It's just he'll need to ping me when he joins so I can give him sharing permission, because at the moment he wouldn't have sharing permission. I don't see him logged in at the moment.
No, he's off getting the quad to show you guys.
Right.
So he's down the end of the corridor collecting bits of quad and carrying them up,
okay, all
getting
right.
through a couple of security doors. So he should turn up in about 5 minutes or so. Yeah.
Right, no worries at all.
He'll be on Discord. So yeah.
Yes. All right. So I'd just like to introduce Professor Rob Mahoney from ANU, and he's presenting with Peter Van Gore on a new open visual odometry system that the lab at ANU has been developing, which is producing some exciting results. And so over to you, Rob.
Thank you very much. So I was enjoying the discussion about displaying the rads and the degrees actually earlier too, but this is my turn now, so I'll keep going. So look, we've been working away in this visual inertial odometry area for a few years now, and those of you that were here last year would have seen I gave a talk, and we got in the guy from the T265 to talk a little bit about that unit as well. So what I wanted to talk to you today about is really where we're up to in this, and we've actually got Peter has been doing a lot of the heavy lifting in terms of doing the code and some experiments. We've got some really neat experiments that Tridge helped us run. We were flying last Sunday, and we got some data to show you from that shows you where we're up to, and then we'll talk a little bit from there. So this talk, I guess we're going to split it into sort of 3 bits, where I talk a little bit about the underlying motivation and how it fits into modern thinking in filtering. So there's a little bit of maths in there, but I'll try not to bore people with it. And then Peter will talk a lot about some of the practical issues and give you a bit of an impression of where we're coming. So just to talk a little bit about what's the academic field sort of looks at in this space. So there's this whole sort of field of visual odometry or spatial awareness, and it sort of includes 3 topics, which are these 3 topics down here. And so it's an interesting thing from the academic community, right? There's a lot of focus on this first topic, on simultaneous localization and mapping. You might have heard about it. All of these 3 topics have a lot in common in terms of the mathematics. But it's really the third of those that's most interesting to the ArduPilot community. So the point about simultaneous localization mapping is it's a problem where you've got a robot and it's moving around in the world, and really what you want to do is, after the robot has flown through that world, you want to be able to rebuild a model of where you went. So it's that there was a group of people did it a few years ago, build Rome in a day, take photographs of Rome, figure out where all the cameras were, reconstruct 3D model of the whole of Rome. Well, they didn't quite do the whole of Rome, but they certainly did quite a lot. And when you've got a robot actually moving, it gives you a lot of construction. So the point about that is it's really not about knowing where the robot is, it's more about building a map. And so that's not really our focus for the ArduPilot community that we're working on at the moment. So then there's what I was really talking about last year, which is visual odometry. And the point about visual odometry is that you don't try and add the inertial measurement unit into it. You just try and use the pure camera to build a model of where you've been and where you're going in the world. And so that's a very interesting academic question. And interestingly enough, the actual mathematics of that problem is easier than the mathematics of the inertial odometry, which is the last one. But the practicality of it isn't there, right? Because if you do have an inertial unit, you should be using it, and you get much, much better results if you do. So from a point of view of actually putting a piece of software on a drone, you'll never be flying without an inertial unit. You couldn't anyway. So you should be using that data in what you're doing. And interestingly, that perspective that I was just talking about is some of the issues that we've been starting to tackle, where we've come in from the academic point of view with an algorithm. Now we're having to deal with multiple time domains on the filter computer to the ArduPilot computer, and remove time jitter and estimate time lags and all of the reality of actually making these systems work robustly in the real environment. So the problem that we're really interested in is this final one, which we call VIO, and that's where you've got an inertial measurement unit that you're getting the data from, and you've got other sensors potentially like barometers and magnetometers that we're going to be wanting to include, and then you've got access to a camera, and usually with the other requirement, access to a camera and enough processing power to do something with the images that you get in. And so this is the results that we got in our group, and hopefully this works. So this is an academic data set. So it's a data set that's generated by the University of Zurich in Switzerland, and it's called the UROC data set for anybody who knows these data sets. So it's a data set that was built and designed specifically to test these sort of algorithms, right? And so they took off inside a room, as you can see, and the quadrotor flies around. It does lots of turns. But what stands out in a data set like this is there's environment all around the drone all the time. You're never high up and looking down at the ground, which is actually a bit of a singular case for most visual inertial odometry systems. And the other thing for this data set is they give ground truth, which is how we benchmark how well we do. But they also provide very, very good quality calibration. They have high quality IMU. They have very fast IMU data. So it's sort of like an ideal, it's a real data set, so it's got noise, but it's a really nice data set where you don't have to worry about calibration and such like. So we're running the algorithm that I'll talk a little bit to you about today on that data set. And these are the state-of-the-art results around the world, right? So at the top here, so this is the room. This is a Vicon, a LiDAR readout of the room, just to give you a bit of a feel of what was flying there. This in the top left is a little quad that they were flying. The data set's about four years old now, so that would be a quad from about 2016 or so. And these numbers are root mean square error. So they're how far away your trajectory is from the ground truth at time t, take that number, square it, integrate over time, and then take the square root of the whole lot. And so if you get a number here of what we've got in that first data set, so these are the data sets that we tested against. So we're on average 7 centimeters away from the true position of the quad doing that, right? And so you can see the sort of the numbers that we're getting. And these are the state-of-the-art, the various state-of-the-art algorithms that are out there doing things in the way we're doing them. So this is using filtering technology, which has the sort of computational load that you can put on these sort of systems. And so just to get a feel for how that looks on the actual thing, if I run this and zoom up to the end and then just pause it for a moment, you can see the blue is the true trajectory and the red is our estimated trajectory. And so you can get a little bit of a feel that, you know, the actual visual inertial algorithm is working really, really well. So what I wanted to do then for the rest of this talk, so I don't want to bore you too much with some of the technical details, but I wanted to try and take a tack through ArduPilot history to explain and give you a perspective on why what we're doing is going to work and why it works as well as it does, and then come back a little bit towards the end and let Peter talk a little bit about how it actually works. So and what we're doing, present a few of the results flying on a quad last Sunday, which of course we're very proud of. So at the end of the day, the take-home messages of what we're doing is to respect the geometry of the problem and to exploit the symmetry. And so this is something that I've been doing from way back. So those of you that have been with ArduPilot from the start would know that there's this underlying filter that sort of sits there in the attitude estimate and provides sort of a backup basis for attitude, and that's a DCM that came out of work I did way back in 2005, and it provides a little bit of a perspective on the whole perspective that I'm taking in all of this work. So the way to sort of see the difference is to think about how you might filter for attitude. So how do you estimate attitude, right? And so one way of thinking about estimating attitude is to consider the angles, the roll angle, the pitch angle, and the yaw angle. And so everybody thinks in terms of these Euler angles. So it's the way you conceptualize attitude, right? You know what a roll looks like, you know what a pitch looks like. So you can think in that way, right? And so that's sort of the most natural way to conceptualize the attitude of a vehicle, but it's not the most geometric way of understanding a vehicle. And we sort of know that from roll and pitch, right? If you roll 90 degrees and then pitch 90 degrees and then yaw 90 degrees, it's sort of the same as doing them in different orders, and it all gets mixed up, and it doesn't make sense. Roll, pitch, and yaw only makes sense when you're making relatively small rolls, pitches, and yaws, and that's all to do with the fact that it's an incorrect geometric representation of the actual object. So the actual object is a rotation matrix, right? And so the actual object that represents attitude, if you take roll, pitch, and yaw, you can create this 3x3 matrix by taking cosines and sines of the various roll angles. So I think the roll angle here is A, the pitch angle is B, and the yaw angle is C. And you create this horrific big mess of all of those angles, and you get a 3x3 matrix. And if you stop thinking about the roll, pitch, and the yaw, and you just think about that matrix, suddenly things become beautiful, right? So in particular, the angular velocity, so this is the roll pitch in yaw angular velocity. So this is the angular velocity around the x-axis, this is the roll, around the x-axis, so that's roll, around the y-axis and around the z-axis. So there's this sort of structure that we can make a 3x3 matrix, and then the actual kinematics of the rotation become this beautiful equation here. So this was some work that we were doing back in 2005. And so we said, okay, well, if that's such a beautiful equation for the kinematics of attitude, why aren't we actually using those kinematics to build the observer? And so we have an IMU measurement, so we can put what we call an internal model, which goes in here. And so that gives the sort of the best estimate of what we expect to happen. And then we add on to that this correction term. So something to basically look at the measurements you've got and make R hat go to R. And so that's sort of the idea of the observer that's embedded in the DCM, and indeed embedded in all of the EKFs now. But the really important part, the thing that makes it work really, really well, is this idea of looking at a specific error. And so this is really nice when you look at the matrix structure. So this error E is a matrix. It's a 3x3 matrix. You think about, you don't measure this directly, but you can analyze the problem in this way. So you think about having the true attitude here, which is a 3x3 matrix, and your estimate attitude here. And what you get is this really nice structure whereby the kinematics, so the evolution of the error, no longer depends on your IMU at all, right? So if I take the derivative of this error, I'm going to get sort of R omega in this first bit. And then when I take the derivative of R hat to the -1, I get this minus, I get an omega. I won't go through the maths, that's not necessary. But the real interesting part is the way that you get this beautiful, beautiful set of kinematics out at the end. And so then we did some stuff, and we did the DCM filter, and the multiplicative EKF for attitude is based on this. And that part of the EKF filters that Paul's been doing over the last 10 years or so is also, utilizing these ideas really strongly. And it all comes down to respecting the geometry, right? So this really is a case of not using what we conceptualize as a human roll pitch and yaw, not trying to impose that on the way we actually do the algorithms, but instead going back to the mathematics of the algorithm and finding the elegant representation that actually works. So that's actually where the DCM came from. And if you remember back in those days, the DCM was so exciting because at the time, people had been building attitude estimators usually using the Euler angle representations, and they were infernally hard to tune, right? There were I remember there was years and years there, about 5 years, where people just couldn't make attitude run reliably. And then we came up with this trivial filter, which has its problems, mind you, and that's why we don't use it these days. But it's robust. It never breaks, right? And it never breaks because it has this underlying respect for the geometry of the system. All right, so I just wanted to make one comment here in that how you build the error is really important. So this error here is an equally valid error, right? So what you want to do with this error is you want R to equal R hat. And you can see that if R and R hat are the same, then the error is equal to the identity matrix, right? And so that's something nice that we can build a designer on. Okay, and we have the old error here where the star is, the two stars on either side, and you can see that this error is R hat to the -1, and this error here is R to the -1 R hat. And interestingly enough, just that little change changes the aerodynamics. So when I take the aerodynamics of this equation, right, I get something which is still not terrible, but it's not as nice, right? Remember in the other aerodynamics, I had cancelled these terms out, right? And so there's this underlying concept, which is that it really matters what error you choose. All right, and so when you tackle these navigation problems, you need to think about what geometry to use and what error to use. And if you get those right, then you start building these very robust, very powerful filters that actually work extremely well in practice. And that's what we're doing. So now I want to take a little moment to talk about inertial navigation systems and what actually is going on in an INS system, right? So the key thing that you're trying to do in an INS system is estimate the position of the vehicle, the velocity of the vehicle, and the attitude. And of course, I'm going to write the attitude as this 3x3 matrix, right, which encodes the roll, pitch, and the yaw. And a few years ago, there was this really cool geometry that came out, which encodes all three of those in the one block matrix. And this is the matrix here, this one here, and it's super cool, right? It wasn't me that came up with it, by the way. I actually found the same geometry a few years after it was come up with, but this was developed by a guy called Bonneville, who's in Numira at the moment, working with his wife there, dodging COVID in France. Anyway, what's so amazing about this is that you can take the INS equations and you can actually write them as a matrix equation. So if you think about the INS equations, right, it's x dot equals v, v dot equals g plus the rotation of the body fixed frame acceleration, right? So this is the acceleration that you measure from your IMU. This is the rotation that then puts that back into the inertial frame rather than the body fixed frame. G is the gravity vector, so it's, the little g 9.8 times the down direction. And so that would be the kinematics of your system, and then you'd have your R dot equals R omega cross. And so normally in INS filters, people write down those three sets of equations and start working with those equations. And this matrix allows you to write that out just in one matrix equation, right? You can sort of see it that if I take a derivative of this term here, I'm going to get R times omega, right? I'm going to get the R omega cross term. The X dot here is going to be equal to, well, there's a 0 here, but I'm going to get V times 1. I'm going to get the V coming out of that term, and then RA comes out of that term. I'll let you, if you're interested enough, I'll let you do it afterwards. But the point here is this is like mega cool, right? That equation, admittedly, I'm an academic, right? And I find interesting things amusing and enjoyable, but this is such a beautiful equation that it really is something worth using if you can. So then the INS equations can be written as this really, really compact and simple to understand equation, right? Where the U matrix here is going to capture some IMU measurements. So it captures all of the stuff from the IMU, and the V here is going to capture the actual state velocity information that you need and the gravity information. So the external information and the state information that comes into it. So you get this very beautiful equation here, which we can use to build our observer, right? So again, this is an observer that respects the geometry of the problem, right? So we've got this really cool geometry and we can do something with it. So again, we can now use this error, which is just beautiful, and we can look at the error kinematics and start asking questions about designing observers. So that's the equation that we get here. Now, this isn't quite as easy to design as the attitude problem. And this is why I actually didn't figure out how to do this back in 2008, because I didn't know how to do it at the time. Sylvain Bonneville actually developed these equations sort of through the 2010 to 2015 period. And interestingly enough, even though it's not exactly what's going on, it is really closely linked to what is actually going on in the ArduPilot EKF3. So this geometry is being exploited in the ArduPilot at the moment, not through the route that I've explained it, but through other routes that have got the same approach. So the trick that is used to be able to design decent filters here is to linearize these kinematics. And the neat thing is that because you've got this unified way of understanding the problem, you've got a unified way of putting local coordinates on the problem, okay? And so this is a trick, which is to say, okay, I've got this geometric error, which is of a very high quality, and what I'm going to do is I'm going to have a really neat way of putting some coordinates on that respects that geometry. So not just any coordinates, but coordinates that respect the geometry. When you do that, you get, in the linearization, you get this equation. And the point about that is that within those coordinates, that linearization is actually exact. So this approach actually reduces the filtering problem, not to a linear problem, but to something that's as close to linear as you can actually get. It's time varying because the linearization depends on the velocity, right? But it is very, very close to linear. And so because it's very, very close to linear filtering methods work. And that's where the EKF3 is actually, it's working in this sort of space. So given that you have such a nice linearization, then you can throw, and I won't explain standard Kalman, but this is just a Kalman filter for a time-varying linear system. And what you do is you design the innovation using the filter, and then you lift that innovation back to the actual geometry of the main system that you are dealing with. And so the filter that you get is designed based on linear filtering principles, but the actual implementation respects the geometry. And so those filters, that's basically what's going on in the ArduPilot, and it works extremely well. So this gets us to where we're going with EquiVIO, right? So in a sense, you can see the progression, right? Back in 2000, 2005, we knew about the set of rotation matrices. It's actually a classical Lie group, which has been known about since the 19th century. But the geometry of it really was worked out in the early 20th century, and people have been using that geometry ever since. So when we did that work, we just had to go and pull that off the shelf. The INS problem, to understand it, really understand it in this geometric way, needs a Lie group that's that SE23 that I'm talking about that's so cool, this guy here. It needs a Lie group that wasn't a classical group. So this is one that Bonneville came up with back about 8 years ago. And so the recognition that that is a Lie group and what it actually does is quite new. And with it, you can get this gorgeous interpretation. And in parallel to actually understanding that interpretation, people have gone ahead and got that geometry through anyway, as clever people do. And that's where the multiplicative EKF goes and some of those aspects. But it provides a sort of a coherent way of understanding what goes into making those filters work so well. And now for the EquiVIO, what we've been doing for the last about 4 years is trying to figure out how to get a geometry that works for visual inertial odometry. And last year we managed to crack that. So we had worked out how to deal with visual geometries a year and a half ago. So that was last year's talk where we were coming from. The problem was that the geometry has to also incorporate the inertial parts. And we managed to crack that mid last year. And so we've just got to the point now where we're able to actually build algorithms based on the principles I've said and see how they work. So the key thing that we're doing here is we've got this new geometry and this new symmetry. So we're going to pose it on the group. We're going to use the symmetry for the error, and the reason it's going to work well is that the linearization that we use then for the filter design is exact. So I've got a slide here which really I don't want to waste your time with, but I guess it's worth just mentioning a couple of things of what actually do you have to do VIO, right? So VIO is all about the inertial state of the robot. So these are the inertial navigation states, right? Rotation, position, and velocity. And then when you use the camera, what you're going to do is you're going to estimate something in the environment. And at the moment, the way we do that is we estimate a series of points. So each PI here is an element of the environment. So it's a point in the environment. And so that's what the algorithm does, right? So and of course, the rate of change of a point as long as it's attached to the environment, is equal to 0. So what we do is we look in the environment, we find a static point that we can see recognize in the image, we track it over time, and then in our state, we estimate the position of the point. And by estimating all of that together, we can actually see motion of the robot through the space. So the geometry that we use is, the first part is the same SE23 geometry for the inertial states. And then we have to introduce a rather unusual geometry on these points. And it involves a bit of a rotation matrix, which isn't the state of the robot, and a scaling factor. And the reason we've got these two parts of the geometry is that when you have a visual bearing of a point, the symmetries of that bearing, the things that you can do with it symmetrically, is you can rotate the point and you can scale the point. But you can't through the view of a camera, because the camera is a bearing. You can't actually do a 3D transformation in a symmetric way. So you have to split the understanding of how you deal with points into rotations and translations for every point. And that's sort of the underlying symmetry that we're talking about. And again, look, I'm happy to talk to people if you're interested. I'm just trying to give a high level view of what's going on. So a really last word to talk about. So, I mean, that's all I want to say about the reasons why things work. But I wanted to take just a moment to talk about what goes wrong. And not what goes wrong in the practical sense, because Peter will talk about that, but what goes wrong theoretically. And a really important thing goes wrong with visual inertial odometry, and that's that you actually can't tell the difference between the points being in a different place and your robot being in a different place, right? So it's exactly the same thing if I see a whole bunch of points on a sheet on the ground and Andrew Tridgell goes and grabs the sheet and pulls it sideways, and at the same time the robot moves. Everything from the point of view of the robot is the same, right? I have no GPS, so I can't tell the difference between moving the points and moving the position of the robot, right? And the other thing that you can't tell is yaw. So you can't tell if I rotate that sheet, the difference between rotation. So you've actually got yaw, this yaw here, and position that are what we call unobservables. So you can't actually observe them from VIO. Now, this is a bit of an issue, right? Because the whole point about VIO is what you want to do is servo control position, right? You want to use it to tell you where you are. And so what we actually end up doing is we estimate as much as we can. So all of this subject to the fact that the position and the yaw can't be estimated. And so one way of thinking about that is that you don't estimate this, but we actually have a slightly cleverer way of just estimating the information we can and then estimating what's left. But it does mean that the algorithm that we have has two parts. One part, which is a filter, and the filter itself has a part of the state that's still unobservable after the filter. And then what we have to do is do a secondary optimization to determine those parts of it. And mathematically, this diagram here sort of represents what's going on, in that there's a part of the state here, which is this flat sort of curvy surface, so the manifold, you might call it, that you can estimate, and there's parts of the state that you can't. And I've got three trajectories here, a red trajectory, sort of dotted yellow, and a dotted green. And from the data, you can't tell those trajectories apart, right? Any one of those trajectories could have caused the data that you see. Okay. However, so what the filter does is it estimates the equivalence class. It estimates the information it can do, and then what we do is we have to have this separate algorithm which rebuilds an estimate of the actual trajectory. So when you see the results that we're getting, we've actually got two things going on. One of them is this filter, which is as robust as the DCM and working as well. And then secondarily, we've got this extra optimization step, which is sort of reconstructing the position and the yaw of the vehicle from an assumption. And the assumption that we use is that the points in the environment aren't moving. So if you do have a particularly annoyed Andrew Tridgell there pulling the sheet sideways while we're trying to fly, then we've assumed that the ground is stationary, and so we'll simply make a mistake about where we are. So don't use a VIO algorithm over the top of a train or something like that that's moving, because it's just breaking the underlying assumption of what's going on in the world. So I had a little bit of a chat about why equivariant VIO work, and I appreciate you your patience in listening to me, because I know I tend to be a bit academic. What we want to do in the group is we want to take this filter, which we believe is the best in the world, and we want to take a step from running it on these academic examples and proving that it works academically, which we can do now, and actually roll it out as something that everyone can use in ArduPilot. And so what we're running into is the reality of all of the issues that come up about making a piece of code that the mathematics works really well, but now actually making it work well in practice. And that's where we're really coming to the ArduPilot community. This next year, we've actually got something now that we can start testing. What Peter's going to talk about now is a whole bunch of stuff around, what we've been running into and how we've been solving the problems. And then we're looking for feedback about, what do we need to do to really make this become something that everyone can use. So I'll end there. Peter, are you around?
Yep.
So I'll press stop share. Did I stop sharing there?
I think so.
Great. Okay, Peter.
I'll start on mine. Yeah, so as Rob mentioned, I'll talk a bit more about the practical obstacles we came across in the last 2 weeks trying to take this algorithm from something that works great in theory and works pretty good on nice academic data sets and needs to work also now on real ArduPilot data. Right? So there are a lot of things to consider, and I'll give a shout out to Michelle, who did quite a bit of this work last year in her honours thesis. So questions around, okay, the board that you're using to your ArduPilot stuff probably isn't strong enough to run VIO. You might want to have a companion computer. Then you, of course, need a camera to be able to do anything visual. And what camera should you use? What properties should it have? And finally, one of the issues that we came across, particularly in the last 2 weeks, was the issue of the different time domains between the MAV, which is sharing the IMU data with your companion computer, and the time on your companion computer. But I'll talk to each of these points in turn. So first, our hardware. We're flying a custom quad rotor. So Rob's here. He's got the quad in there. Nope.
Yeah, that's good enough. Oh, it's mine.
I don't know why you're...
Don't worry, I can see
okay.
it. Yeah.
But yeah, so we have the quad. There it is in the picture, right? We have a companion computer. We used a Raspberry Pi 4. And we also have a ELP global shutter camera. If anyone's really interested, I can give you the model number later. Okay, so choosing a camera, one of the things we know is there are two things we know are important for visual odometry, visual inertial odometry type algorithms. The first is a global shutter. So that means that every pixel is fired at the same instant. And what this prevents in particular is sort of tearing effects. When you have fast motions and you use a classic rolling shutter, this half of your image is a little bit in the past relative to this half of your image, which is no good when you're trying to do an algorithm that assumes everything's happening at the same time. The other thing is that we want a wide field of view. So we want to be able to get a lot of information around the robot, and this really helps with motion estimation. So I mean, there's a reason that our human eyes can see something ridiculous like 130, 140 degrees, right? And it's because it really helps us, estimate our own motion. And then what I'm showing you in the videos is we had to try and tune the exposure of the camera ourselves. And this can be sort of challenging. So, however, there are existing computer vision techniques, in particular histogram normalization, that can basically get around this. So you can, in the top image, there was a bit of flashing, lighter and darker of, there you go. While the bottom image remains relatively steady. So the bottom video is processed from the top video. Okay.
Paul Riseborough has a question about the isolation of the camera.
Oh, sorry.
Sorry, I noticed that the camera appears to be isolated separately to the frame in ArduPilot. Was that angular changes in angular alignment cause you any issues?
I'm not sure what you mean by isolated separately.
Well, I saw that the camera was sitting on a little test fixture and it's on with the rubber mounts.
Yep.
To the airframe, but the ArduPilot's on the top of the airframe. So in other words, you've got an angular alignment difference between. It could potentially change alignment between the camera and the ArduPilot where the IMU sits.
Yes, and this is a very important point. I'll talk more about it on slide 9, I think. Okay. But in general, right, you can never put your camera and IMU in exactly the same spot with exactly the same axis alignment. And the calibration of the relative rotation and translation between them is a really important part of making visual inertial odometry algorithms work well. So for those of you who've played with the RealSense T265, which does visual inertial odometry on board, they have an IMU inside their camera, so they know exactly how to align their two visual cameras with their IMU. But of course, we want to make something that's a bit more accessible to everyone in the community, and everyone's going to put their camera in a slightly different spot. So yeah, I will talk about calibration. Okay, but for now, I wanted to mention the time domain differences. So the first thing we know is that, of course, both times are measured by a different, on a different computer, right? The MAV will give me a time stamp, which is some microseconds since boot. And then I have to translate that into a time on the Raspberry Pi. So that time lag is an issue, and we need to try and compensate for it. But aside from that, what we found is that there's also a jitter in the time delay. So this is just because the IMU messages coming from ArduPilot through to the Raspberry Pi, sometimes the message comes very quickly, sometimes not as fast. And so what I did is I left the quad sitting there for an hour, recorded messages over the whole time on the Pi, and compared, okay, well, what's the, so setting the first timestamp for both the MAV and the Raspberry Pi to 0, what's the difference between all the relative timestamps? And so what you see is there's a distribution, and it's roughly plus or minus 2 or 3 milliseconds with a few outliers. That's going on. Now, Tridge and I have been talking. He has a really nice algorithm to try and compensate for this jitter. And we're very keen to work on that and implement that in the future. The other thing that we saw, which was interesting, was the slow drift of the relative time difference. So for the time scale on which we're flying of a few minutes, this doesn't matter that much. We're talking about 5 milliseconds over an hour of on time. That's this slope in the bottom graph. But of course, if you wanted to do visual inertial odometry for 10 hours or a whole day or something, you would have to realize that by 10 hours, you're going to have a 50 millisecond time shift purely from the difference in time scale between the Raspberry Pi and the MAV. So this is another practical problem that you just don't have to think about in the academic data sets. In the academic data sets, you get an IMU, it has a timestamp, you have images which have a timestamp, and they're exact. So how do you calibrate all these systems? So we have effectively 3 things we need to work out. We need to work out the IMU noise characteristics. And we're not very keen on trusting the data sheets in this case. We also need to work out the camera intrinsic parameters. So this is things like the focal length, the image center, and things like that. And the last thing, perhaps, well, one of the most important ones is working out that alignment between the camera and the IMU. So these things, as I emphasize on the slide, should all be straightforward, but they tend not to be. Well, I mean, the IMU noise and bias are. So we model the IMU as having a Gaussian white noise and a slowly time varying bias. You can find both of these just by doing an Allen deviation plot. And so these are, well, that's what's shown on the right. And that gives you the noise and bias parameters. So with our quad, we found the accelerometer is a bit noisier than the gyroscope. But yeah, neither of them are particularly terrible. Okay, but knowing these noise parameters is really important to identifying that alignment between the camera and the IMU. So how do you calibrate a camera? Well, you choose a camera model and then you use one of the standard calibration algorithms to find your camera parameters. So you can see in the top, we have the uncalibrated video, and what should be straight lines look like curves. So you can see the edge of the desk is really bow-shaped, whereas in the bottom image, all the straight lines are straightened out. So this is a rectified video, which is important for making sure that the assumptions we make about the geometry of what the camera sees are actually satisfied in our algorithm. So one of the problems is that, so the pinhole camera model, which is what we decided to use in this case, works very well for the center of the image and not so well for the outside. So you can notice as well that the bottom image actually cuts off a lot of the information around the edge of the top. You can see it cuts off way lower than the top image. So there are other camera models which can do better, but they don't have quite the same number of calibration tools immediately available. And so that's why we've gone with pinhole for now. But investigating fisheye camera model or a double sphere camera model, which is a nice piece of work from a few years ago, is one of the next steps as well. Okay, but this calibration really is sufficient for at least the center of the image, and we can always crop out the outsides, even if that does reduce our ability to do the motion estimation perfectly. Okay, now in terms of IMU and camera offset, this is where this is typically done with a big optimization algorithm. And so you take your IMU data, you know that the offset, you assume that the offset between the IMU and camera is constant, and then you effectively try and solve for the trajectory of the camera and the offset from camera to IMU. It can be a very sensitive problem. It was solved to some degree a few years ago in the academic community, and they released a really nice software package called Calibre, which is still on GitHub, and it still works for Ubuntu 14 and Ubuntu 16, but has not been updated. So it's very hard to get it working now. It relies on a lot of out-of-date packages, and it's not really set up to be able to handle losing particular packages. For example, Sean, a guy I was working with, tried to use it to calibrate our IMU and camera, but the system failed because it couldn't find a graphing package for displaying the results. So we solved the problem a bit differently. We estimated it roughly, effectively by hand, by saying, okay, well, we know where the IMU frame is. We know roughly where the camera frame is. So now we put in some parameters into our configuration file, and then we solve it more accurately using our filter tuning. And that's the next thing I wanted to talk about. So on the right, I've got a picture from one of the configuration files for the Equivio system. And as you can see, there are a lot of parameters. And unfortunately, the performance of the algorithm is quite dependent on choosing sensible parameters. So what we did so first we tuned it manually by hand by choosing sensible values for each of these things. And that's not too hard to do, but the end result of the filtering isn't very good. But what we realized is the fastest way to tune it is just to take a flight, look at the GPS data and say, well, we want to match the GPS data as best as possible, and then simply run an optimization scheme overnight that changes the tuning parameters, runs our algorithm, compares it against the GPS, and slowly but surely finds optimal tuning parameters for our situation. And so this, if you have a reasonably long flight, your quad will or your UAV will see a bunch of different situations, and you'll be able to let it tune itself on your computer. And then you'll have good parameters to fly the next day. So that's what we did. And we set ourselves a goal to do some skywriting and write EQF and underline it. And then we wanted our EQF algorithm to estimate that trajectory really well. So as I mentioned, the real data is more challenging than the academic data sets. And that's why we had to do quite a bit of work to get to this point. But we're very keen to try and write some notes on our experiences and make it a bit easier for other people who want to get into visual inertial odometry and using this sort of algorithm for state estimation. So the videos on the next slide are our results. They're not time aligned, but they show off what's going on. So in the top left, we have the actual view from the quadrotor. In the, it's left the audio in. Has it? I'm happy to have it fly slower. Oh. Oh dear, it's not. Okay. The top left is the view from the quad. On the right, we have the trajectory. So the the GPS trajectory compared with our estimated trajectory. I'm happy to have it fly slower. I'm sorry, it's, I thought I'd cut out the audio from my recording, walking videoing the drone on the ground. Coming up on the end of the E.
Don't worry, Peter. Just go on.
I'll just go on.
That was my commentary.
Anyway,
I was on the ground station and I was explaining to Peter where we were in the skywriting as he was so the different parts of the lettering.
Great. I really thought I cut out the sound. Anyway, the three different views. So you can see the trajectories line up very nicely on the EQF. We can underline it at the end. And one of the things I'll point out on the next slide as well is the. I'm going to go to the next slide. There we are. Okay, so apologies for the talking over it. That was to show you what was going on, right? So we flew for over 200 meters, and in the end, we achieved what we call root mean square error of 1.75 meters. So we, as academics, are very happy with that. The other thing that's worth pointing out, that's interesting, that's missing the underline.
The truth data isn't necessarily truth. We weren't using an RTK GPS, which we should have done, because there could be some error. It was just using an ordinary M8 GPS. And so it would be perfectly believable, in fact, expected that there be more than a meter of error in that position from, it was really the EKF3 solution it was using. There could easily be more than a meter. There probably is more than a meter of error in that.
Yeah, so, and as you can somewhat see from the alignment, I mean, there is some error in the X and Y positioning, but there's substantially more error in the altitude as well. But yeah, so these are the results of the filter. And we're keen to, well, there's plenty more work to do to improve these results. I think we can still do better, but it's a good indication of where we're going. So in terms of future work with the practical implementation, I'm very keen to try and remove the jitter from the timing. So that should help improve the using the IMU signal. There are lots of different camera models, and I expect that people in the community will want to use lots of different cameras. So I also don't want to set it up to only work with fisheye or only work with pinhole or anything like that. We want to be able to support a variety of different camera models. Now, another important thing is, of course, it's all good and well that we can estimate the position and attitude of our quad, but we want to give that back to ArduPilot so that ArduPilot can actually use that in lieu of a GPS signal. Then, as I mentioned, the calibration is quite challenging. Well, the camera intrinsics are easy. The IMU noise is easy, but the measurement of the IMU to camera transformation is difficult. It really is. It's easy to get wrong if you do it by hand, and a small error in the attitude alignment especially makes a huge difference to the performance of the filter. So if I change the angle by a few degrees, that can reduce the increase the error in the filter by a meter, for example. Then another thing we were interested in doing is looking at fusion of other non-GPS sensors. So in the academic community, people are very focused on just the IMU and just the camera, sometimes two cameras, if they want to go for stereo. But in practice, even if you are GPS denied, you might have your barometer, you might have a compass, you might have a rangefinder, something like that. So there are a few other sensors that we really could try and integrate as well. And finally, again, the academic community runs these algorithms on something like the Euroc data set, and there are 10 sequences in that data set of about 2 or 3 minutes of flight each. And you know that's of course pretty much no time at all compared to how much flight is being done with ArduPilot every day. So if we want to roll out this VIO, I expect there will be lots and lots and lots of testing for all different setups. And I'm very excited about that as well. I think that'll be a great opportunity to really develop this algorithm into a robust solution that works for everyone. Okay, and finally, special thanks. Tridge helped me fly everything last Sunday, so greatly appreciated. As well as all the discussions about timing jitter were really interesting. Thanks a lot, Tridge. Michelle actually sort of built that quad, or at least set up the companion computer and the camera, and a lot of the software interfacing between ArduPilot and the Raspberry Pi last year. I don't know if we would have managed to get our demo ready in time without the groundwork that she'd done. And finally, Sean is another student here who's been working with me on this. He's not here today, but yeah, well, he helped get it all running. So thanks a lot, and let me know if there are any questions.
Well, congrats on getting that working. That's really impressive.
Thank you.
Yeah, really nice piece of work. I think we should fly again with an RTK. And what I think we should actually do is have multiple EKF3 lanes. One of the lanes set up to use the RTK GPS, which means the EKF solution could be considered truth. And then a second lane set up to use the cheap, affordable M8 GPS, which means, and then we have the VIO solution, and that gives us in one flight truth plus how well it can estimate with a commodity GPS and how well it can estimate with a commodity camera. And that actually gives us a real comparison for, is this in the same ballpark, particularly over an extended flight? If you could do like a 20-minute, half-hour type flight, just by throwing more battery. And we do have a vehicle out there that could carry a lot of battery. I'm thinking the Lift Octo that we have from Canberra UAV. That's the one we're doing the water gliders off. It could actually fly for quite an extended period of time. And that could be like a definitive data set that includes essentially truth data like you would get in a Vicon, but out in the real world with comparison to what an EKF with a commodity GPS can get.
So this is another interesting point about what sets these geometric filters apart a little bit. And Rob briefly mentioned this, is that the fiber structure Rob was talking about, where we have a smooth base space and then this secondary optimization. It's a really important part of what makes our algorithm work, and in principle is what is really important to our algorithm being quite robust relative to the existing works. So in the existing works, you don't separate this structure, and you end up with unbounded growth of uncertainty, which in principle, it might not kill your filter in 5 minutes. It might not kill it in 15 minutes, but eventually your filter will stop working. The corrections it'll make to itself will be too extreme. Whereas what we do by using the fiber structure is our uncertainty on that fiber structure always remains bounded. And then the secondary optimization doesn't have the boundedness problem. And so I think gathering a long-term data set, a really sort of 30-minute flight or something like this with good GPS RTK truth data would be a super interesting experiment, and maybe a real contribution to the academic community as well.
It should be super easy for us to do. Now we've got this set up. Next few weeks we could go out and do that. Gather that data set if you've got the time. It'd be fantastic to get it, I think, and see how well it does. I'm interested in the handling of moving features. So, you know, out at Spring Valley, for example, the bulls and the horses are probably wonderful features, right? But it's inconvenient to tie them down because they don't really like it if you go and chain them down during your flights. So they do actually walk around the field. But I imagine that the visual odometry thing would look at a bull and think, that's a great feature, nice little angles and things. There's the horns I can lock onto. You know, that horse over there, that's a nice feature.
For sure, for sure.
How big a problem is that? I mean, could we eventually use this, you know, in a farm environment where you have cattle and sheep and those sort of things?
Does it run a median? I mean, if you've got a lot of points there. So if some of them are moving around, if there's some form of a median filter.
Yeah. So let me jump in. One of the things in the state-of-the-art visual inertial odometry and VSLAM that goes on in what they often talk about a front end and a back end. And in the front end, they identify points and they track points. And then there's this big chunk of code which we don't want to write, which basically goes through all the points and says, oh, this is attached to a cow, it's moving, throw it out, don't use it. You know, this is attached to a car, or this is moving, or this is unreliable. And so it's and then it also does the data association. So it says this point is the same as that point was in the last scene. And it's a really big chunk of code in a lot of these algorithms. And it does improve results, but in those algorithms, it's really critical for robustness that if you don't do that, you end up with instability. And we actually think that because we've done the geometry properly, we can still be robust, but just have a slightly less reliable solution. So it's one of those things where it's a, you know, we're writing a piece of code that we want to work for everyone, right? And so what we don't want to go down a rabbit hole where you end up with a big complex piece of, you know, logic that's trying to do something too difficult, because it's just going to break, you know? And so we're actually thinking about things like actually, instead of using points, just expanding that out into big chunks of space. So particularly for flying vehicles, where a lot of the time you take off and then while you're down close to the ground, points are great, right? But once you take off and you're 30 meters up, a lot of the ground just looks like a flat sheet, right? And so if you can find a flat sheet and just match bits of flat sheet, that's going to be much more reliable, and that's going to take out some of these things. So that's how we're thinking at the moment.
Yeah, I think that's a really good point, Rob, because you're much better off having a performance that degrades more gradually and is less brittle. And the problem I've seen with the algorithms you've mentioned is that they tune them up for really nice performance on their specific data sets. And then when the algorithm fails, it fails spectacularly.
Yeah. Completely blows away,
Yeah.
So you're talking about other sensors incorporating. Is it worth incorporating an optical flow sensor to help with the rejection of some features because you have a basic velocity over the ground? Does that make sense?
So at the moment, one of the things to point out is that in the video we took on last Sunday, we actually have a moving object, namely the leg of the quadrotor is visible in the camera.
Yeah.
Right? And that isn't static in the world, right? It's moving along with us. And my algorithm's very happy to pick up some features. It's a black leg and lighter background, so it's great. The simple solution is just a straightforward outlier rejection, which says, I have some estimate of how I have moved since the last frame. And if the points are really not where I expect them to be, then it's probably not satisfying the static world assumption. So that's how we've done it at the moment. There are more sophisticated solutions that might work a little bit better, but I think that's the most practical thing to do. When you're talking about flying over a huge group of cattle, it depends, right? If 80% of your screen is taken up by moving objects, that might be very challenging. but as long as you've got mostly static environment, it should be okay. In terms of adding an optic flow sensor, I think it would suffer from pretty much the same problem.
Yeah, different scales, I guess. The thing I thought of is currently you're using the raw IMU Mavlink message, right, coming in, which means part of the problem with that is that's been filtered quite aggressively by ArduPilot, and it's filtered in a way that the user controls that change the filtering to suit the, their tuning of it for attitude control. It might be worth instead to be shipping across a delta angle and delta velocity, which is what the ArduPilot EKF infrastructure uses. And that would mean it wouldn't suffer from that problem of user configurable filter for, the wrong task. Would that make sense?
Yeah, so I mean, intuitively, you always want to filter on the on sort of the rawest signals available. So, but we can have a longer discussion about which signal exactly do we take from the IMU.
Yeah, it's actually an interesting point in that the whole thinking that's gone into our algorithm up to date has grown out of the systems and control community. It's all based on continuous time analysis, right? But the reality is that everything in a computer is in discrete time, right? It's all quantized and discrete. And there is a theory there to do discrete time versions of this, to do forward integration exactly so you get delta angles rather than actual IMUs and all of that. So, I mean, being who I am, of course, what I want to do is do the proper mathematics of it and do it properly. But I'm also aware that maybe we should just like jump in and do a few hacks and get something working. Probably in terms of resources in our research group, it's going to take us a year or so to get around to the actually solving the discrete time problem properly. And maybe we should do something in the meantime. I mean, this is one of those things, right? I've got different agendas. One of the agendas absolutely I want to engage in over the next year is making this work for ArduPilot and start to roll it out, because I think the algorithm's there now. But I've also got my eye on the academic sort of markers for the future too. Yeah.
Yep. I'm really looking forward to us closing the loop. I'm slightly concerned about the delay, because there's going to be a delay. The IMU data coming out of ArduPilot going across the link to the Raspberry Pi, the VIO processing on the Pi, bringing it back, and then ultimately it's going to be fused in via our VIO methods, via our sort of external navigation, data, velocity, position, etc., into Paul's EKF, and the total delta of that time, I don't yet know how many milliseconds that's going to be. The discussion I had with you last weekend, Peter, was quite encouraging. You thought it was down in the milliseconds range, not the hundreds of milliseconds.
Tridge, I was giving that some thought, and there's a two-way perspective. I mean, the VIO can afford to run it, provided it's able to buffer some of the data so we can time align the inertial data coming across. I assume it's doing some time alignment internally. So its calculation is on a delayed horizon, and then we take that back to the EKF, and the EKF is set up to be able to handle something back in, swallow something back in on a delayed horizon. So as long as we've got a common definition of time and time stamping, it's all very doable.
Yeah.
How accurately can we get that? Can we get it to a millisecond?
So, Paul, in principle, if you start messing with the hardware and go into you have direct MIPI access to the camera, you've got common clock across camera, sensor, image processing CPU, and potentially even the ArduPilot side of things as well, you can get that delay down probably sub-microsecond without substantial amounts of difficulty. Now, that's going to say that you're going to have to probably leave the Pi and go to something like IMX6 for your processing. You're probably going to you might have to go to a Sony sensor, for example, just because there's drivers for that. And then in terms of synchronizing the clocks between all that, there has to be some sort of common clock structure, whether that's going to be a pulse per second and everything phase lock loops off that from GPS, or whether or not you're distributing a 10 megahertz or 25 megahertz base clock for everything, and then doing all of your clock magic.
I think we can use the jitter correction and then have a base time. So I think it's quite doable.
Yeah.
And I'd like to stick to the commodity hardware for the moment and demonstrate it on hardware that is easily accessible within a modest budget for our community. And it'd be great to have a high-end version of it as well, right? To demonstrate on a high-end one what can be achieved if you can, buy great hardware. But what's so attractive about this is, Raspberry Pi 4 plus, I gave a link in the chat to the particular camera. It's just a camera I found on eBay that is loaded on this copter, and it's a $70 camera. 70 Australian dollar camera, so it's toy money, and that plus a Raspberry Pi 4, that's incredibly affordable, and we really want eventually like a wiki page on you go and buy this camera and you get this Raspberry Pi, you connect it in this way, follow these instructions, and you've got a great VIO system, and that. It's getting to that first stage and getting it replicated out so that members of our community can actually achieve this themselves, that we'd focus on that, I think, initially. And as well as, of course, generating the data for the academic stuff for Rob and Peter's papers, where we want some truth data and RTK and that sort of thing. But making it readily accessible to anyone who's got the room to have this little camera and a Raspberry Pi is just so attractive.
I would love to try something like this on my quad plane setup with the VTOL.
Yeah, fixed wing with the higher velocities on fixed wing will be interesting. I'd love to fit it to a small fixed wing, which will allow us to get much longer flights. And like hour or so sort of flights. It's just a matter of how well it handles like the turbulence and the high, velocity. Because it's further off the ground, you don't tend to fly really low with a fixed wing. I presume that it's really the flow rate that matters for this algorithm as opposed to the actual absolute velocity. Would that be right, Peter?
The tracking is the issue, and the worst thing you can do is a very fast attitude change. So if you do a very fast roll on a fixed wing, so the number of degrees per second that you've just put into your camera, of course, is pretty high. And if your camera frame rate is only 20 or 30, then frames a second, right? You might get hundreds of pixels of displacement on your image points.
We do have a method for the optical flow. Paul added in a method for where the EKF actually tells the navigation code, don't fly above this speed because I won't be able to track.
Yeah.
Right. Oh, okay.
Yes.
Right.
In fact, I found I had to do that, not only putting in limitations in terms of speed to respect optical flow limits, but also and height limits, but there was also code put in there which we wind down the gains on the position controller. The feedback that you get back, because you can end up with an attitude rate causing a slight perturbation in the state estimates, which feeds back to the position controller, and you end up with a loop.
Yeah. So one of the outputs of your filter should be, what the navigation limits are, and then we feed that in to ensure that we don't violate them, so that you don't lose track. And that's already in place for copter. It's not there for plane at the moment. The fixed wing code doesn't honor any of that stuff. We just ignore it. And it's partly a problem because, that code might say, oh, you can't fly faster than 5 meters a second. And the plane will go, well, in that case, I'm not flying anymore. I'm stalling. So, there has to be, we can certainly do roll and pitch rates though, as long as we don't violate our geofences because we can't turn fast enough. But
Yeah, I mean, one of the things I'm keen to do with it is I was looking at Randy's talk from the other day and the switching and everything. So one of the things we can do is we can absorb the GPS as well, and we can actually we can lock our filter to the GPS, so we can use that as an innovation, while we're running, and then if the GPS switches off, we're already synced to it, right? There's no need to resync, right? So because we absorb the IMU anyway, we can just absorb the other stuff from the ArduPilot, and then switching back. If the GPS switches back on, you need to think about then we'll have our estimate. I mean, what the filter does then, I guess the EKF could do the same thing, right? Absorb us and then phase lock that. Because it just takes a little bit longer to respec the GPS again.
Yeah. The other thing to think about is the definition of yaw angle in the frame of reference, because if we're just using the VIO to fly the vehicle and we're not using GPS, then it doesn't matter. I mean, the definition of yaw with respect to, what is your world frame? Where does it align with respect to true north? It doesn't matter. As soon as we start fusing in at the EKF level for the main navigation filter, start fusing in world frame measurement, then your alignment between the two frames matters.
Yeah, but I can pull we can pull the state from the EKF, right? And just put an innovation on that state into our filter and at a really low gain, so it doesn't really disturb the filter, but it just locks our filter onto the, basically onto the base reference of the EKF. So
okay,
that would be what we should do, is we just get our filter, because our filter is basically floating in space, right? So the VIO, you can rotate it and translate it any way you want without actually changing the underlying filter. That all happens in the fiber.
Yep, I like that idea. That sounds good. It's going to make things simpler. And I guess the only thing that's shared between us is the fact that we both agree where gravity is.
Yeah. So we can't lie about gravity, and you can't lie about acceleration. But you can lie about position. You can lie about yaw. Yeah.
In fact, you don't. If your system doesn't actually need the GPS data for some reason, I mean, obviously, in this test, you were definitely, looking at the GPS so you could compare, versus reality. But from the ArduPilot point of view, just like the T265 has no idea about the GPS, of course, and so we had to deal with that in the ArduPilot side. So we like I said in my talk, we have a rotation, we have an offset that we can handle on the ArduPilot side if that's necessary.
Yeah, but it makes sense because basically all of this stuff just goes into the fiber adjustment that we're doing. So the filter doesn't change at all for us. And then we can just use the GPS and just make sure that where we are on the fiber is locked onto the EKF, right? And then if we lose that, that's fine. We're already there. Yeah.
Really cool.
Absolutely fantastic. It's really exciting. It's
really
great to see the progress on this. And Peter's been working very hard the last week. There's been a lot of progress. I'll have to ask you later, Peter, how did you solve that Z problem that I saw during the week?
I'll take responsibility for the Z problem. Peter just
okay.
Yeah.
It was confession time.
I thought of a really clever idea and it was shit.
Right, okay. Well, I'll love to hear the story on that later.
Absolutely.
All right. Well, this has been absolutely fantastic. I love that talk, and really great to see the progress. I'm looking forward to doing a lot more flights with you guys and closing the loop.
Sounds great.
The next big milestone is to close the loop, so it's actually flying under VIO control, and it takes off and lands in the same position, and goes out and does a tour around Spring Valley, and comes back and lands in the same position, and there will be a huge cheer when we get to that point. So fantastic.
Really great. I just also want to add that I think, if we do what, Trish was describing, set up a wiki page and tell people, how to set it up and where the code is, and, maybe make an AP sync image or something that helps them to get started quickly. I'm sure there's going to be a rush actually of people to give it a try, whether, that's good and bad, because then you get all these questions and stuff, and, maybe we could help, handle some of those questions and stuff, but I'm sure you get a lot of interest because we have a very active vision projects channel in ArduPilot, and there's people trying all kinds of things, so I think if we have a system which works, even if it's not like perfect day one, you get a lot of interest and people, trying it out and uncovering, where it works and where it doesn't work. I think it'd be really, really exciting for everybody.
Then we should have a corpus of data that we publish that other researchers can use. So we really should publish it with a set of vehicles, not just one vehicle, but like a dozen different vehicles in different conditions, preferably with truth data with RTK, and that this can be used as a basis for developing these algorithms and improving them over time. So we have to make sure that the logging and the data capture that we have built into this process is sufficient that we can then use that data and bring it in as part of a corpus for the research community.
Yeah. Yeah. I mean, and I think if we had the setup easy for the community, of course, included in that, and maybe this is what you're just saying, but a bunch of other researchers, our community has all kinds of people. It has professionals, it has DIYers, but it also has significant research group from all over the world and stuff. And those guys, I suspect most of them, don't want to, they want to get to the core algorithms. They want to get to the hard part first, and this might help them get there faster. If we have the proper instructions and stuff. So really, really exciting stuff. I'll do my part.
Yeah. I mean, the place where we've published some papers, so we're happy to have all this go public now. The spot which I think we need to knock over in the next few months to make this really work well is all of these sort of underlying issues, like how do you do calibration? How do we port the OpenCV? How do we get Calibre so it works, for everyone rather than 4 days of installing old versions of libraries? How do we port how do we port the OpenCV for different camera models, the calibrations, all of those things, right? We need sort of basically to bring all of that together and make it all work pretty seamlessly. And then, the goal here is that anybody can just like put a Raspberry Pi on, put a camera on pretty simply and get data and make something work, right? And whereas if you can't do the calibration well, you just can't turn the thing on, right?
Yeah.
So we've got to hit that. Then the algorithm's pretty robust. Then we should have something that we can start then building on. Yeah.
Brilliant.
Good. Thanks.
All right. Well,
also probably you'd have to integrate it with GPS failover, like what Randy was doing, right?
Yeah.
Because one thing I was wondering is how does the algorithm degrade with the number of features? In other words, as the number of features go down, is it more or less linear, the degradation? Let's say I'm on I'm flying somewhere with a quad, not too high, and next thing I know, I am flying over a patch of total green, 0 feature. What happens then? You would, does it just try and stay in place, or does it completely lose its bearings, or wouldn't you?
It doesn't break immediately, right? Because you've got the IMU, so you essentially continue flying on IMU. If you have 0 features, things are going to fall apart reasonably quickly. I mean, you forward integrating IMUs isn't a particularly good idea ever. So roughly the degradation is going to be with the square root of the number of features. So, if you go from 20 to 10 features, so square root, 25 to 16 features, there you go, you'll drop by 80%, right? Your accuracy will drop by 20%, right? So usually we run around about 20 to 30 features. That's what runs. Once you get down under 9 features, you're about half. You're starting to lose accuracy, right? But there's very few situations where you can't see nine points that are reasonably stationary.
Because it's a very wide field of view camera.
Yeah.
Right, but let's say it may seem like a corner case, but water. I mean, that's going to do it, right? I mean, you got a lake in your mission, your history. Technically, well, there may be a few boats, I guess, but
you
get my point.
I'm interested. Yeah, I'm interested to see what we can do over water. I'm super keen to get some data and have a look, right? I mean, if there are ripples and they're not moving too fast and they're all moving the same direction, you'll be able to pick up the ripples. And then what will happen is, well, what will happen is the whole world will be moving with the ripples, right? So
And if there is nothing in a way, I mean, it's not a total failure because a human being wouldn't be in the same situation, right? I mean, if you have 0 feature, and that's it. You just can't go on anymore.
Something it's worth mentioning, and it didn't come out in the talk from yesterday, that with this drag fusion in the EKF, you can actually turn that on, and actually, if that's running all the time and you build up a wind drift, then if you lose your GPS, you can actually fall back to almost like a wind relative navigation with a quadcopter. Now, it's a bit drifty, and it tends to but it will constrain your velocity area to about 2, maybe 3 meters per second. So it'll stop that accelerating flyway and extend the amount of time that we can go.
Yep, good point.
Yeah. That's exactly what we should do. That's great.
So I saw there's another question in the chat about fog. In general, right? If you don't have visual information, you cannot correct your IMU drift. The same problem happens if you fly very, very high and far away from objects. At that point, a meter of motion will hardly appear in your visual information. And so that also is just impossible to correct for.
Yeah, the origin of this question is there's a couple spots within short driving distances of where I live that have fog that will hug the ground. So for example, if you're on the highway, you'll be driving, you'll come down into a canyon and boom, visibility goes from miles to 0 in 2 seconds.
Yeah, so it depends, right? If you're flying inside the fog and you can't see anything, then too bad. If you're flying above fog, as long as there are things like trees sticking out, you should still be able to run on those.
Cool.
All right.
Yeah.
So that absolutely brilliant and greatly appreciated. So for those of you unmuted, I think a round of applause for Rob and Peter.
Very kind. Thank you.
Thanks.
Really nice, guys.
Really good work. So
Thanks a lot.
we're now moving on to the next talk. So we have Michelle. I'll just switch the recording just a second. All right, all done. So the next talk we have up is Michelle, who's going to be talking to us about the newest vehicle type addition in the ArduPilot world, which is support for blimps. So over to you, Michelle.
Yep, so just screen share. So can everyone see the slides?
Yep, all good.
Cool. Everyone, thank you for inviting me to do a talk here. So of course, I'm Michelle and I'm presenting on Blimp support for ArduPilot. And so this is some of our prototypes so far. So yeah, it's just a quick about me. So I'm doing a master's degree at UNSW with 3 in math. And so there's some info as well. So this is what I'm going to be covering today. And so we're just going to kind of go through reasoning why, and then hardware and software and things. So they're also known as airships, of course, just helium balloons with some form of propulsion, usually props, not in this case. So because they don't need any power to keep them in the air, so you can get long flight times depending on how you've got everything else set up. So they're useful for the indoor application as well, because they don't get damaged or crashes easily as most other drones would. So even with the fins, like I've run it into walls and it just bounces off. So you have the relatively low airflow that's caused by the blimp itself, where with any like multi-rotor, if you fly it over the disk, you're going to have papers going everywhere. So using the fins instead of the propellers also helps with that. So yeah, so it has a larger amount of air that's moving slowly, instead of having yeah, a small area where it could blow things around. So there has been previous interest in adding Blimp support to ArduPilot, but up until now it seems no one's gotten to it. So we kind of thought, well, we'll give it a go. So as far as applications, you could be searching for a gas leak in a building, and then you would hopefully be able to track the gas leak, because you would likely not be blowing it away quite as quickly. Any questions?
So what sort of mass are these blimps, the one you're working with?
So at the moment we get about 50 grams of lift. So yeah, the weight is quite the limiting factor. So yeah, all of the parts kind of, we choose them with that pretty much first priority.
Yeah, that is very, very low mass.
Yeah.
It's difficult. We were just having discussion in the chat there about, combining the visual odometry with a blimp, and I think the weight, putting the Raspberry Pi 4 and that camera on a blimp, it's not going to get off the ground very well, at least on the blimps that you're doing.
Yeah, the Pi 0 maybe, but whether it's possible to do good VO on that low processing power, yeah, it remains to be seen, I guess. So now onto like the initial hardware tests. So most of the project so far has been hardware troubles, and just because of that low weight limit, really. And so we started with a TNC 3.2, just writing Arduino code pretty much. So we had tests between the fins on the gondola versus directly attached to the balloon, and this photo shows one of the initial one of our very first prototypes, which was using fins that had been previously designed for this, or someone had previously tried using. So we've been testing different types of fins, trying to find good ways to get thrust go. So our servos are close to, but not quite 180 degrees. I think it's around 150 degrees. And so that's also difficult, because when you're flapping them, you don't quite, you can't point them straight down, so you lose that range of motion. Balloons have also been fun, because latex ones just explode very easily, and so you can't re-inflate them, which means you end up going through a lot of helium. And they also deflate so quickly that we couldn't keep neutral buoyancy within like a 5-minute flight. So that was quite a big problem. And so the bigger foil balloons we had trouble getting a hold of. This is some of our setups we've had so far. So from top to bottom, left to right is kind of the chronological order. And so that's the first latex balloon, and then we had a foil balloon, but we had to attach another balloon on top of it because this size wasn't big enough, so we ended up finding a bigger size, etc. These are the newer fins we're using which turn out to be a lot more effective. So then finally on to getting it into the Blimp, which has been quite a learning curve and everything. So we've implemented it as a separate vehicle because of the pretty different flight dynamics and things like that. It's still very preliminary at the moment, so because I've only been going for about 3 months on the Blimp, on the ArduPilot, so in terms of getting Blimp in it. So the initial PR was merged just over a week ago. Thank you. And yeah, so thank you to everyone who's helped with getting it this far. So essentially just had Copter as a template and then get the code that would be common as to most vehicles to kind of keep the structure similar to the other vehicles, hopefully. I should probably pause for questions again.
Yeah, there were some questions in the chat. There was a Paul, do you want to explain your question about the flexible fins?
Oh, yes, I was just, when I saw the original picture for the balsa ones, the solid balsa ones, I was asking, would they be more efficient if they're allowed to flex towards the trailing edge like scuba flippers? And then I saw your next model with the flexible membrane, and it looks like there would be some trailing edge flex there.
Yep. So I looked at both the balsa wood and the other ones and thought that's not gonna end well. And so this was initially just done as a trial in one of our fin thrust tests. And so I guess, so this one does flex towards the end. And so that we ended up getting something like 50% extra thrust out of these, like same size fin on the same servos. So that helped a lot, yeah.
How fast these fins move? What sort of frequency are you operating it at for the flapping?
So at the moment, so with the thrust case, we found about 3 Hertz was the best frequency for these fins. But that'll depend on the servos and the fins you're using. So if you're using bigger fins, then you know, slower frequency is where you get the most thrust. So that's a parameter in the implementation at the moment. Yeah. So so in the so there's a fins class now that's used for actuating the fins, and so each servo has the values for its amplitude and offset depending on what the income it gets. So roll pitch, yaw, and height in this case. So yeah, this is for each fin. Yeah, when you're going down, you would need to be flapping both of them upwards so you can push yourself down. So the front and the back ones would flap upwards. Horizontal, of course, is just flapping whichever one's on the opposite side. And so for yaw, you again would offset them both, you know, to the clockwise direction and flap them so you can go the other way. So that's what this bit of code does. So that's the values for amplitude, and that's for offset. And so it sets how much of each stick's input should go to the each fin's amplitude and offset.
Sorry, it's Randy. So I guess the way that the control works is the left and the right fins, they give you like rotation. Is that the idea? Yep. And the forward and back give you like altitude control, I guess?
Yep.
Okay, cool, thanks.
And so, yeah, so kind of putting those fins on double duty, I guess.
Cool, and you don't have to worry about roll and pitch control, is that right? Because it
yeah, it's yeah, because of the just weight at the bottom, it centers itself.
Cool.
So yeah, the input multiplied by fin matrix. So you end up with the amplitude and offset for each fin. We've also added a turbo mode for height and yaw control. So when it gets to the maximum end of what you're pushing, it doubles the frequency, which is just to try to add some extra speed because it does move quite slowly. But it's optional as well for depending on you know what you're using it for, I guess. So all of the values of amplitude and offset for each servo is just put straight into a cost function and then output. So these amplitude and omega are in, so they've amplitude is 0 to 1 and offset is -1 to 1, but it's just multiplied by the RC scale being used. And so we've just added manual and land modes. So manual is directly to this fin mixing code, and land just stops the fins, which is really just for fail safe. And so I was just going to show why the frequency kind of needs to stay the same. This is what happens when the fins are not exactly in sync. So you end up with it just wobbling and not really moving far because the two are adding to each other. But if they're moving in sync, then they mostly cancel each other out, so you get less wobble on the height in your control. For next up, we've also been asked by the Navy Research Lab in the US to build and send a couple of blimps over them to be flown during their Defend the Republic blimp flight competition. And so that's been sent over, and the competition's happening this week. So we're also working on adding the autonomous function. So initially just PID controllers directly to have as simple as possible a controller. And then we'll later look at whether we can use some of competition controllers instead and have a, much more complex and I guess effective controller. So depending on how similar the dynamics is, and yeah. So also working on adding a CITL implementation, which at the moment CITL is working for testing of servo outputs and that, but there's no dynamics added into its model. So it just moves kind of oddly or mostly stays in one spot. So adding the full dynamics to CITL will be great for testing the autonomous function. So we're kind of doing that in parallel with the autonomy. Are there any questions?
The 50 grams limitation on payload, that's for the bigger one, or that's?
That's with the bigger one.
Okay.
So that's about so the balloon's about 0.5 meter in diameter. So we're kind of getting to a point where we can't go too much bigger because then we won't be able to fly it down corridors or things like that. And since this is for indoor use, it's
Because that's what I was gonna ask next is why don't you go with like 2 meter or 3 meter? You want to do this inside, it makes sense.
All right. And so I thought I'd finish off with a flight video just to kind of show what we've got working so far. So hopefully that's coming up for everyone. But yeah, that gives kind of an idea.
Yeah, that's coming up fine. So that's with the manual control, isn't it? So basically the sticks are directly controlling the amplitude on each axis. Is that correct?
Yes, so the sticks control both the amplitude and offset. So height and yaw add the offsets to it. And I've got this stick mixing with the fin matrix happening there as well.
Yep. So it might be worth, even Leonard and Paul and other sort of control people are on the call. It might be worth discussing a little bit about the cascaded pit architecture. So Michelle and I had a bit of a discussion about that. I think it was last week. And I was suggesting that the first level should be an acceleration, a 2D acceleration controller PID, and then build velocity controller on top of that. Leonard, would that be how you'd do this? So basically,
you've got to be. Oh,
I'd be careful with using acceleration feedback because of the 3 Hertz input, and also the fact that the motion is very heavily damped.
And that's exactly what I was going to say, probably less eloquently. Is you got to be very careful going too far down in the to a too lower level, and like accelerate, like trying to directly control acceleration is only really appropriate if you can control it very well. And as Paul says, because this is very heavily damped, your primary output is probably going to be largely proportional to the velocity you achieve. So trying to go to a level below that and control acceleration is actually going to probably make things terribly difficult for you.
So you're thinking instead go first level would be a 2D velocity controller with just a very long time constant?
Yeah, just set your filters appropriately.
Right, okay.
And your output's going to be approximately proportional to velocity, even in that case. So your feed forward term in your velocity PID is actually going to be your dominant control parameter. So you set your feed forward to be your output actuation magnitude versus your target velocity or your measured velocity. And you'll be able to actually initially tune your entire PIDs to 0 and base it just on that feed forward parameter.
Right,
and
a bit like the way we do heli.
Yeah,
yes.
And if you wanted to account for things like air movement in buildings due to HVAC, in the periods when you're not actually moving the fins, any movement relative to the air is going to produce a drag force, which we talked about yesterday. And I think the EKF with a pretty minor modification would be able to estimate the wind drift around the vehicle. And that would certainly help with that, working out what the feed forward needs to be in terms of the movement, because it's going to be very sensitive to air movement in the building.
Well, that's going to be really the I term off, like that's going to be your constant velocity. So that'll be that will tend to get taken up by your I term.
Yeah, but that I term is in an inertial frame of reference, not in the body frame.
Yes, very true. Yeah, so you'll be able to add your velocity command to account for the air movement, as opposed to change your feed forward. I was thinking feed forward parameter, that's the multiplication of your target airspeed, target velocity versus the output actuator magnitude. You're talking about the actual amount of velocity you request. Well, the amount of output actuator.
It's the amount that you request, because basically this thing flies relative to air.
Yeah,
very much so. And so you're going to have a demand in earth frame, and I think we'd probably need a velocity integrator, an integrator in earth frame of reference in terms of accounting for the effect of air movement in the building.
Yeah, and this is actually one of the reasons I'll talk about it in my talk, but part of the architecture changes to the position controller in Copter was to explicitly enable applications like this with the additional tuning factors to do away with a lower level acceleration loop. And so that's got the integrators and the feed forwards in at the velocity level, so explicitly so to deal with aircraft like this.
So Randy's just mentioned, suggested starting with altitude control. So would the same thing apply at the moment the Copter has an acceleration controller at the lowest level for vertical, right? And you would go straight to velocity vertically as well and skip the acceleration stage of that loop vertical?
Well, one of the things to keep in mind about a multi-rotor is the output actuator is force. So that acceleration control, is very useful for and we've got a very fast feedback loop around that, so to allow us to accurately get a specific acceleration vertically. So that's quite useful. Whereas if you don't have that, it's actually often easier just to work based on your velocity. The other thing is our output actuation. Whether you're doing a velocity of 5 meters per second vertically or hovering, the output throttle doesn't change much, and you'll get a peak in the throttle, and then it will go back down close to.
Whereas with this, it's going to be very much a very strong relationship between throttle setting and the velocity you asymptote to.
Yeah,
right.
The other interesting thing about having done a little bit of work with something lighter than air in the past was that when you're talking about a non-streamlined shape, you end up with what's called the actual effective mass of the vehicle when you start accelerating is actually higher than the calculated mass, the displaced mass of the vehicle, because it's it's essentially accelerating the air around it. So you end up, when you do the calculation, start analyzing the data back to try and do system ID and what you think the mass is, et cetera, you end up scratching your head and wondering why you come out with a higher value than the mass of the vehicle. It's the apparent mass effect.
I'm very glad we asked that now, because I was sending Michelle totally down the wrong path, which is why you shouldn't get a software engineer to make advice on controls. Michelle, I think forget everything I told you last week and listen to Leonard and Paul.
Yeah, apparent mass effect. It was that was worked out theoretically back in the 1920s with all the airship when they had an explosion of airship technology. Pardon the pun.
Yeah, there were a few explosions back then.
The trouble with added mass stuff is it'll change drastically depending on, if you're in a big room, it'll be approaching a sphere in open space. If you're in a corridor, it'll be hugely more.
Oh yeah, that's right. As you get close to the wall,
yeah,
exactly, it becomes higher. And that brings up another interesting point, which is, this is spherical, so it's not going to steer in, but there is going to be a pull-in effect as you approach a wall, if you're moving. Anyway, it's a very interesting problem.
Yes, and then capturing all of that in the simulator would be a task in itself. So I was suggesting doing the simulator by just assuming that the fin, you capture like the position of the fin and its angular velocity, and you presume it's producing a force along where the hinge goes in, and it produces a torque perpendicular to the surface. And then just shift that out for the position to calculate the total torques and forces, and basically run that at a kilohertz or so to do the dynamics. Is that a reasonable way of capturing it, just as if we want a very simple simulator?
Yeah, I think that's a reasonable way to do it, because we can make an assumption about the flexure of the surface, the actual working surface of the fin, and its local movement. It's going to be a very ad hoc sort of tuning factor to do that. I mean, having looked at a few papers with people that have done modeling on flapping insect wings and so on, you can turn that into a PhD thesis if you want to. So we might be better off just taking some measurements and matching
I was
that up
thinking
to
maybe a table might be the right thing to use. Yeah. Sorry, Michelle, is it diverting up onto other areas?
So it's just fascinating.
It's a fascinating sort of vehicle. I'm really looking forward to seeing how well we do the navigation, and getting it to fly figure eights and things in the room, and it's going to be really quite fascinating to see how well this develops.
Got a lot of parallels with a submarine.
Yes,
and
very much so.
Yeah, I like the subcode sort of pretty. It's juvenile.
Choose your words carefully there, Leonard.
Well, you know, it's an adaptation of multi-rotor. Like it hasn't, like, you know, that all of the structures, like we're still trying to set up our structures to support vehicles like that, and the extra, like there's still missing parts to make it easy for them.
This platform has one huge advantage over the sub platform. It doesn't have a cable that people here can tie around.
Yes, indeed. Yeah, never let me on the sticks with these blimps, Michelle. You'll the person who brought the sub to Canberra learned that I'm a very terrible pilot of submarines.
I think it's just generally a good principle not to let Tridge on the sticks.
Yeah, I think so.
Give him the ground station.
Yeah. Excellent. So there any more questions? All right. So we've got one final
on YouTube. There was a question on YouTube which said, let's see, what is the propulsive efficiency difference between a ducted fan blimp versus the flippers? Quote, I wasn't expecting to see flippers when I heard blimp.
Yeah, that might be more for Sridhar, I guess.
Yeah, hey guys,
yeah.
I can just jump in. Just introducing myself. I'm Sridhar, and I think Leonard, we've crossed paths before from RMIT days. I don't know if you remember.
You're muted, Leonard, by the way.
I do. Sorry.
Yeah. Anyway, so as said, you know, as Michelle introduced me, you know, this is something that we were thinking about. I come from the insect flight area where they use flapping wings, as you know. So one of the objectives was trying to see if we can build an indoor flying platform which is going to be, you know, crash resilient like insects. So the idea is now the reason we went with fins, or that we wanted to explore fins, was the problem with the prop-based blimps that I've flown before is, one is, you know, you get lots of these oscillations because the propulsive, the dynamics of the propulsive system is an order of magnitude different from the dynamics of the plant. So you end up with this motor doing, you know, not what it is designed to do, and usually sort of burns out very quickly, or it gets very noisy. And so to avoid all of those, and to, you know, come up with an innovative platform to get everyone a bit more interested in blimps again, so we said, hey, look, why don't we try fins? And it also goes down to what I think Leonard mentioned about subs. You know, the idea is, could something like this be a controller that we design on ArduPilot for blimps? Could then that be transported to a robotic fish, not even like a sub, but a robotic fish, which is more, you know, which has fins and things. So it's along those lines. So there's a bit of innovation quotient going on with the platform itself, but also the fact that hopefully this will then, you know, get more people excited in the community about blimps and ArduPilot, and how do we add support to this apparently new vehicle class.
Yeah, and propellers get tangle things. I mean, any thread or something in the water, in the air, particularly underwater vehicles, they're always swallowing things and getting choked.
Yeah, right, exactly. So so even for the underwater you know, environment, maybe a robotic fish might be a more suitable you know, propulsion strategy. And the idea is, you know, if this blimp or this fin-based blimp method, could we then transport that or adapt that for fish?
ArduFish.
ArduFish, yeah, I know.
Yeah, I like all of these vehicles. So this and sub, and any of these, the other 6DOF vehicle that Peter, no, sorry, I apologize. Somebody jump in and help me.
Pete Hall.
What was that?
Pete Hall did the 6DOF.
Yeah, the other Hall. You know, these multi-rotor, these navigation, a lot of these things are sort of doing a lot of stuff with the multi-rotor code, and we still have to add some of these the translation parameters from our basic navigation code to allow these vehicles to easily integrate with, like if they're going to build off of multi-rotor and the multi-rotor navigation, to actually facilitate those types of, you know, the full 6DOF actuated vehicles. They're not aircraft anymore. They're just moving in a medium as opposed to a multi-rotor that's really just a 2.5D aircraft. So yeah, I'm really happy to see another vehicle sort of pushing us in that direction.
Fantastic. All right. Well, thank you, everyone. I think that's been a fascinating discussion, and looking forward to seeing how blimps develop over the coming months and years. And then I'd love a fish to go in Lake Burley Griffin. I think fins on a fish and getting it swimming around. You know, if we can get it done for the next Dev conference, that'd be great. We have the sailing boats on the surface and the fish underneath. But there's a challenge for somebody to build a viable fish with fins. And as Paul said, don't let me on the sticks. So thank you all for this. Been a great session. So we've now got a break. And the next session, the fourth session of the conference, starts this evening Australian time. So that would be, it's now just coming up to 2 p.m. in Canberra, and it starts at 7 p.m. So 5 hours and 10 minutes from now. For those of you who are in a time zone where you're able to stay awake for that long, welcome you all back to the next session. And the first talk we have in that session is from Andy Piper, entitled Good Vibrations. And following that, we have Pete Hall with his 6-off copter. That's you've probably all seen the famous video of that flying about, and he's going to be talking about the design of that and addressing some similar sort of navigation issues that Michelle was going to have to address with blimps in the coming months. After that, we've got Tim Whitehand. The next morning, we've got Tim Whitehand with Transwing. We've only got 2 talks this evening. So see you all in a bit over 5 hours, and enjoy your break. Get out in the lovely sunshine if you're in Canberra, and look forward to talking to you all then.
Thanks, everybody.
See ya.
Thanks, everyone.
Bye-bye.
Thank you.
Bye.
Thanks, everybody.
See you guys.